Okay, so guys, let's get started. So Bruno, did we start with Bruno, the registration? Okay, so guys, welcome everybody to the research increment number 20th. So it's been a long journey so far. My presentation will be, yeah, that's the crowd arriving. Yeah. Okay, so once again, welcome everyone to the research increment number 20. My presentation will be short and to the point, so that we will try to get in schedule for a tight agenda. So 4 bullet points, really quick: an update on the team, an update on the projects, an update on publications, and a couple of messages. So the first one, a team. So in this increment, we Omar joined the team, and Omar joined the DARWIN team that is now focusing more in on evolutionary aspects on parallel devices, and we were also expecting Hani Ahmed to join the research unit for the ErgoCub team, but basically the hiring date has been delayed for visa issues, and anyways, we will be having Hani in the next 3 months, most likely focusing on sim to real aspects. So then a quick update. Leonardo started the meeting. Do you see the, just to check, can someone connect and check if the presentation is visible? So we on the links. Okay, great. So an update on the project. So we are getting to the end of the Honda Joint Lab, and basically it's been another exciting. There have been another exciting 3 years, and I wanted to thank Mohamed and Stefano for all the work carried out during these 3 years. Clearly, also with the support of Giulio and the Delta team. But basically the main development was coming from Mohamed, and and now we restarted other discussions for possible extensions. And Honda seems to be more interested in on computational aspects for basically parallel computations. So that's why basically the Darwin team has engaged onto these possible extensions and discussions. So we already had a preliminary discussion with Honda guys, and we will see where we get to. So an update on publications. So I usually do this because what happens usually is that we know very well the literature on the other side of the world published by another university in, I don't know, Cuba, and we don't know what is going on behind the corner. So the paper by Carlos has been also accepted to ICRA. Carlos, I saw him around. Yeah. So very congratulations, Carlos. Really nice results. So not only the robotics automation letters, which is a journal, then the paper was also accepted to ICRA. Then we got another acceptance to ICRA, which is Saverio, and which I don't know where Saverio is. Yeah, Saverio is there. So Saverio, congratulations. It's been the output of the master thesis and a long work. Well done, Saverio. And then there is another update that basically the paper by Mohamed on online nonlinear MPC with stability guarantees has been accepted to RAL, so robotics and automation letters. This also was a really nice result, and it was really nice to see how the algorithms could work not only on the ErgoCub, but also on the quadrupeds by the DLS research unit led by Claudio Semini, in a collaboration, on a tight collaboration with Giulio Turrisi, that I also wanted to thank, and that's basically the outcome of the paper. So congratulations, Mohamed and Giulio, for these really nice collaborations that I really encourage. So I really encourage bottom-up collaborations across research lines, research units. Do not hesitate to stop other guys and understand what they're doing. So if there is any space of collaborations, we historically we've been always open, and we will keep being like that. So a few messages. So the first one is that the research increment is getting crowded. Okay, so it will today will be a long journey, and we need to restructure this. Okay, so because we cannot keep basically adding stuff. We are increasing in numbers, so we have to find other ways to gather together every 3 months. So it's basically fully packed, and now we need other ways to organize the presentation and the planning that we do every 3 months. Most likely, this is something that we will discuss with the Scrum Masters, and it emerged, it re-emerged in a discussion with Fabio yesterday. So most likely the idea would be that of somehow shrinking the Scrum Master presentation to highlights, but the details will be discussed with the Scrum Masters themselves. Anyways, it will be, let's say, there will be the intention of keeping the vertical presentations, because these are an exercise for young researchers to learn how to present, how to pick up titles, for instance, of of presentations and stuff like this. Okay, so it is an exercise that we will keep doing it. And yeah, as always, I am a little bit struggling in these days for keeping up with the one-to-one. So do not hesitate to call for one-on-one, and we will have our private sessions to discuss about any problem that you need. So once again, the one-on-one are still struggling to be put on the agenda. But if you need 10 minutes, if you need 15 minutes, if you need 45 minutes for any particular reason, do not hesitate to somehow highlight this need, and we will find the time to discuss about anything that you think to be discussed. There is always the strict intention of avoiding any signal of toxic environment. So in the case that you somehow feel that there is any of this, do not hesitate to talk to me. Okay, so then I think that we can move. We can. I had to pick up, you know. This time I wanted to change, so instead of philosophers. So let's move forward, and we can move to the next presentation, which is by Giuseppe. Yeah, thank you very much.
Okay, Bundi, how are you? So good morning, everyone. This is a presentation related to the control-oriented learning team. So the control-oriented learning team is a team that goes across all the teams in our lab, and the basic mission is to study and explore the integration of learning techniques into robotics at ontology. The rough, I would say right now, forcefully division, let's say, in terms of topics that the control-oriented team is studying can be somehow divided in learning models, environments in robotics. So moving also to behavioral modeling and synthesis. We can also somehow study data-driven methods for design, so co-design, and learning for control, basically reinforcement learning. The groups in our lab are ErgoCub, DTMX, the iRonCub, and DARWIN. And the control-oriented learning somehow picks people that are working on topics related to learning through these groups. Our group is increasing. So we have 3 new additions. These are Davide, Omar, and Arianna. I guess that sometimes there won't be space in this slide. But let's start. So we can start from the first topic, let's say, that is behavioral modeling and synthesis. We can start from the work that Cheng is doing, that is the so-called neural network inverse kinematics, so human joint kinematic prediction. The main objective is to to predict the motion of the human and pass them maybe to the robot, starting the sensors that a human can wear. That is, for example, the iFeel suite. Going more into the detail, we have three main points. So what Cheng is doing is basically framing the problem as a physics-informed network training that is encouraging the adherence of the prediction to the kinematic of the human. So it's using basically the forward kinematics and the Jacobian retrieved from the human model. Then there is also an addition that is called the kinematic optimizer. This works in deploy and in training that somehow constrains furtherly the prediction and minimizes the error with respect to the measurements. And also there is in training phase a manipulation of the PI gradient. Why this is helpful? In some cases, since there are two losses, in this case there is the data, the classical one, and the physics informed loss, these two losses can be competing. So what Cheng came out with is to project, when is needed, the gradient of the physics informed loss on the data one. So these two gradients are less competing, let's say. Now Cheng is in the phase of writing a paper, so he has 9 results. So on the left, we can see the blue avatar, that is the ground truth, and the red avatar, that is prediction 10 steps later. And also prediction is done just using 5 IMUs, one that are placed on the pelvis, the forearm, and the lower leg. And these measurements are used to feed the network that then predicts is 36 joints, 31, and I'm not sure about this. So what's next? In this case, the network, the architecture is just predicting the joints. We need also to predict the base. So this problem will be framed with a base estimation problem. Then we have the work of Evelyn. This is concluded work, the trajectory generation using the physics informed learning. So there are two main components, the physics informed that guides the learning towards kinematically feasible spaces, and also a control-based blending that drives the evolution of the base to, also in this case, to create a smooth transition between motions. So the idea was to extend what was done with the pi adherent to collaborative carrying. This is a work that Evelyn is doing with Mohamed. So the idea is to substitute an operator with a robot. So in this case, a robot would help an operator to carry, for example, a box. The tools are similar to the one presented in adherent, physics informed adherent. And we have two phases, that is data selection. So basically, Evelyn is using the iFeel suite. And then this training somehow with some other physics informed information will be fed to the framework. Now this activity is on hold since Evelyn just left for Manchester. She will work on reinforcement learning, a more mathematical topic related to an operator, but this activity just take off. Also going to a different behavioral synthesis approach, we have the work that Carlo has done, that is XBG, end-to-end imitation learning for autonomous behavior in human-robot interaction. This paper has get accepted. So the idea was to substitute the LSTM as a temporal component with a transformer encoder. So the idea, a transformer network. So the idea is to somehow let the transformer capture sequences and correlation that are also far in time. This work has been carried out with the guys from Pavis, and we already have some results. Okay, so this is a preliminary deploy of the network. So yeah, this ongoing activity. XBG needs to be increased. So we have two streamlines, let's say. In one case is to robust the architecture, And we can do this with more structured data, so feeding to the network the skeleton on the end effector pose. This is a work that Ariana is doing with Carlos, and also extended robot behaviors. This is another activity I just take off, that is to use cross-embodiment, for example, via visual learning models, and to get data from the internet, so adapt them to the iRonCub model. And also following this streamline work that Giovanni is doing, so we have seen another demo that is the one in which the robot, in which the person talks with the robot and the robot is able to answer and move. This is not as simple. The scheme is more or less, it's more similar to this, so the architecture is quite complex. But we have two phases, the training phase in which the training of XPG is done, let's say, from scratch, and the network is conditioned with some labels that are expressing and describing the actions. So in this case, the training is more directed towards some known space, let's say. And then there is also the play phase in which this network is fed by labels, but these labels are retrieved using a large language model. So when you talk with we can see from here, for example, we have this nice video that is recorded. John is talking with the robot. The robot, the speech is translated and then passed through the LLM, and the LLM is able to generate the favorite action, let's say, and also some visual response. So in this case, we enable more channels, more than the motion one, we can enable also the speaking one, let's say. Okay. We switch to some different topic. This is the data-driven method for design. So we can say co-design. This is exactly what Filippo is done. So the idea is to learn how to accomplish a task and evolve the model accordingly. So we can think that we can add to the classical reinforcement learning loop in which we have an action, the reward, and so on. Another external loop in which there is another optimizer. So we have the model that is fed to the simulator and evolves according to the task. For doing this, what we need is a fast simulator, and if it is differentiable, it's even better. So we can somehow use optimizers to get the parameters. But this is the topic of the presentation that Carlotta will have later. So stay tuned. Another approach to address somehow the problem of co-design is the one that Lorenzo is using. So the main objective is to optimize the leg geometry, taking inspiration from the passive walker, that is the strange machine that you see on the left. So there is no actuation there. The robot is just moved by the gravity, let's say, the only energy that comes in place. So what Lorenzo is doing, he started from the analytical model of a walker. This is a 2D model, but he will soon extend it to the case of a curved feet, and then to the 3 case. So he's analyzing the periodicity using also Poincaré maps, for example. The idea then is to optimize the curvature of the feet through some optimization algorithm, for example, a genetic algorithm, and give somehow indications on the design of the leg of the robot. Punit is addressing this problem, but with a slightly different approach. So he's starting from the CAD. So the idea is to use directly some software that generates model and take into account structural analysis, and generate then models, for example, the RDF, pass them to a simulator. So the classical co-design loop. In the previous work that Puni has done, he optimizes for the interfaces with the jets. So the structure that hold the jets. And now is extending the optimization to other pieces, in particular to the interfaces with the external forces, so jets and contacts, so also feet. And he wants also to optimize height and weight of the robot, for example, moving the central mass, moving the masses inside the limbs. How to do that? He's using two main tools. So the assembly parametrization and the structural analysis is done using SolidWorks and Creo, while the topology optimization, so also the modification of the structure of the link, for example, not only the inertia and the mass, is done using Rhino and Grasshopper. How we can do the task evaluation? We came up with this idea. So since the main idea is to also optimize the robot for multimodal tasks, so aerial and legged locomotion, we can feed and evaluate this the model in a reinforcement learning loop that has been done in which the robot can walk and fly. So we can optimize for two main objectives. So I can just imagine that, for example, at the last part of the research unit, we'll add, for example, the wings, se bloccato, wings. But for doing this, okay, si è bloccato. Un attimo. Maledetto Windows. Sempre. Ok, let's start again. Okay, almost there, I guess. Okay. Okay, where we were. So I was saying, I can imagine that at the end of the research unit, we'll add some wings, for example, and the robot also exploit more in depth the somehow the capabilities of an aerial humanoid robot such as iRonCub. But for this, we need, for example, some models, in particular aerodynamic models. This is what Anto is addressing during his research. So he started from this idea, using an autoencoder to learn how the aerodynamics shapes the robot. So basically find a latent space that embeds independent variable that can describe the aerodynamic quantities. So what he's doing is taking data from simulation, but also from real world experiments in the Galleria del Vento, in the so, for example, in this video, we can see how the pressure is acting on the robot in a flow. The autoencoder aims at reconstructing this pressure. So the autoencoder is fed with 2D reconstruction of 3D representation. So basically, what Anto is doing is to unwrap the pressure on the 3D surface on a cylinder that then is fed to the autoencoder. The results are pretty promising. For example, this is the latent space. We can see some structure. So the idea is to continue on this work. So the intuition is that the whole robot somehow affects the single part, and we need to take into account the whole structure. But in the meanwhile, Anto left to Stanford, most likely to continue with this work with a laboratory that is focused on aerodynamics. We had a meeting, so we have a plan for the future. So the idea is to improve the image autoencoding. It's passing from 3D to 2D reconstruction, so reducing the space, and then from 2D to 3D reconstruction. And as you can imagine, some information are lost in this conversion. So it needs to somehow investigate a strategy on how lose less information. But the other idea is also to feed directly the architecture directly with 3D features. We have three main paths. So the first one, the simplest one, is to change the autoencoder from the old structure using a simple multi-layer perception. And then using also graph neural network or point convolution neural network. Why graph neural network? Because maybe the idea is that we can exploit the connected structure of the graph neural network to process connected points, such as the one that we have in meshes. And why point convolution neural network? Because there is no graph in this case, since we work directly, but we work directly on 3D points, so point clouds, and we can use the convolution to connect and create dependencies between these points. And then the final step will be to embed directly the Navier-Stokes equation in the process, so somehow analyze the flow and the volume around the robot to exploit some physics information. Regarding models, we have also the work that Filippo is doing. So the FT modeling and calibration, why we need calibration for FT models, for FT sensors. the raw measurement of FT somehow needs to be transformed. So we need the right measurements. So the idea is to take data, so measured FT branches that are not correct, need to be calibrated, FT temperature and FT acceleration, fed them to a model and have the calibration. And the physics informed information is here is in the use of the model. There are some results that are pretty promising. In this video, you can see that basically Phil is compensating somehow the controller compensates for the motion. With no second calibration, the movement is not really good. There is some damping. While with the second calibration, we can see that somehow the movement keeps the energy. But then also a monster came out. So we have the temperature effect. We see Danny with a strange tool eating up the robot. And from the data, what Filippo discovered is that we have hysteresis. So on the left, we can see that with no second calibration, these are the raw data. We have hysteresis. And feeding the temperature in the model, so do a training with the model, this hysteresis is mitigated, let's say. Along with this, Phil is also investigating the use of STM. So somehow the LSTM should capture some possible dynamic effect in the FT. Before was instantaneous. Right now with the LSTM, we can give some dynamics. And also Filippo find out that there is a slight improvement with respect to the multi-layer perception. We arrived almost at the end. There is now the reinforcement learning. There is MPC for iRonCub. You may wonder if this is connected to learning. No, but Davide will soon start to work on topic related to reinforcement learning, and there will be the presentation later. And finally, this is the work that Giulio and I we are doing. This is reinforcement learning with adversarial motion priors. The idea so is to take some, to exploit imitation learning, have some motions that are taken from motion captures or humans that are walking. They scale them to the robot and somehow create a reward that forces the policy to follow some robot movements. The simulations are okay, and we need to move to the real robot. So what is needed? We have joints with friction, so we need a policy that exploits the friction during the training. For this also we have heavy domain randomization, something more, maybe yes. So more the randomization, for example, with the terrain, maybe more information in the sense of observation that we give to the policy. But we did some first experiments, and it does something. This is the fancy video. We have also another video that I prefer because it's funnier. As Giulio said, we might have broken some FTs. È felice. Okay, and with this, we are done. So I hope that with this brief and not complete overview of the research, some discussion will sparkle later. And thank you.
Prova. Okay. So any question for Giuseppe? Okay. So we choose the let's go with the next presentation from Fabio Bergonti.
Cheers. Okay. Yeah. Good morning, everybody. I'm Fabio Bergonti, and today I'm going to present two things. First, the ankle team, and then the mechanical intelligence. So let's go quickly to the ankle team. So basically, the project objective here is to improve the aerobatic capability by designing a new lower body starting from the ankle. And the goal is to create a new lower body that must enable dynamic walking, clean blisters, and bending to touch the ground. So basically, after some iteration, what we would like to do is to have a behavior like this, kind of, after some iteration. So for sure, we need to improve the hardware and then also the control. And in order to do this, what we started doing 3 months ago was to create a new team that is a team that groups some AMI members and ICAP Tech members. So we are combining research and the expertise of ICAP Tech. And so we started 3 months ago and we did a bit of planning. So we prepared 6 milestones and we managed to complete 4 out of 6. But before going through all of these, let's just have a quick recap. So we want to design a new mechanism, a new ankle mechanism, and we have decided to create a mechanism with closed kinematic chain and linear actuators. So basically we have these 2 linear actuators. When they move simultaneously, we actuate the pitch, while when they move in the opposite way, we control the roll. So now let's move to the milestone. The first one was to create a digital thread in order to implement a model-based system engineering pipeline that will allow us to track how the process will evolve in these approaches. And the first things to do in order to implement this pipeline is to identify the requirements. And so to identify the requirements, what we decided to do, we spoke with the stakeholders that are my people, and we have defined some tasks that we would like to do with this robot, and we have performed some simulation and experiment with the real robot in order to identify the joint requirements. With the joint requirements, we have developed, so we got a lot of data, then we have created the mathematical model of the mechanism. With this mathematical model of the mechanism, we managed to convert the joint requirements in actuator requirements. So we have found the actuator requirement that then are also fundamental in order to choose and design an actuator. But for this task, we have used these requirements in order to create the model engineering, the digital thread to track the system requirements. So we integrated the requirements in this MATLAB environment. So this is for our concern, this milestone that we completed. Then a second milestone was to design a setup to test the linear actuator. So here what we wanted to do was to create a setup, design it such that then we can later characterize the linear actuator. And in particular, we thought of creating a setup where we have a linear actuator that moves a mass. Then we have sensorized the system with a load cell in order to measure the force that the actuator is doing, and then an accelerometer and an external position sensor that works with a laser technology in order to have the ground truth of the position of the actuator. The communication of the of the sensor is done with the DAC, the National Instrument DAC, that then communicates with MATLAB, and then we use also MATLAB in order to control the actuators that send some commands via YARP to the EMS and the 2-fork boards. So with this conceptual design, we started the mechanical design, and we created a first design, and we purchased all the components. Some of them already arrived, and we started assembling it. Then, since all the components that since not all the components arrived, what we started to do was to create a temporary setup where we found some components here and there. And so we created this setup with a Camozzi actuator that was already in the lab, with a load cell that was already in the lab, and also with some accelerometer. And with this temporary setup, we managed to test the communication with the 2-fork and the EMS, and so we started to understand how we can control linear actuator with MATLAB, and so we revived the Double-B toolbox. Yeah, and then another task that we were doing was to identify the main components in order to create the first ankle mechanism, and in particular here, given the constraint that we have found before, we started the literature review, and after a lot of meeting with suppliers, we have identified this actuator. This is the Wittgenstein actuator that is going to we were going to use it in order to create the first mechanism. And basically it's a linear actuator where we have brushless motors connected with ball screws that converts their rotation to linear motion. And basically this actuator already integrates an incremental encoder, and we have chosen to use the incremental encoder because in this way we can control it without changing too much the firmware. And yes, but at the same time, these actuators enable us to satisfy most of our requirements, except for the most dynamical one, that were the jumping and the fast walking. And so what we started to investigate was also the possibility to design a custom actuator. So we are investigating the possibility of creating a custom actuator with ball screws, but also with roller inverted screws. At the same time, we started another investigation where we are also evaluating the possibility of creating a mechanism that has a different kinematic structure, so maybe without linear actuators. And for example, the mechanism that you see in the video is the mechanism of the unitary robot, where we have revolute motor, and also here we are evaluating the possibility of creating a custom actuator with a planetary reducer. Then another activity that we started was the creation of so the idea was we wanted to have a simulation of the low-level controller to track the desired joint position. So we wanted to have a control law that permits us to track the foot orientation and with controlling the actuator. So what we did here was we created a SimScape model of the ankle. We ported in the system composer pipeline, and then we have verified that the simulation the result that we obtained with these simulators are comparable with the mathematical model that we have developed before. And yeah, and they are. And so the next step in order to conclude this activity is to design this controller. Then another activity that we did was the perform a simulation of iRonCub walking with the new ankle. Here, what we found while we were performing all this simulation with several simulation environments, which were Gazebo, Mujoko, and the real life also, that there was a big Cinturium gap. And so what we tried to do was to also port the same controller that we are using on the real robot to Mujoko. And so the guys implemented the TSID controller in Python and tested with Mujoko with automatic gain tuning, and basically the result that we obtained reduced a bit the sim to real gap. And then at the same time, in order to simulate and test the new ankle, what Roberto did was to understand how the force limits of the actuator translate into torque limits, and now what we wanted to do is to integrate this relationship in the constraints such that the controller can provide a force that is that satisfies the requirements, the limits. Then the last milestone that we set was to create a framework in order to optimize the linkage parameters and the actuator selection here. So what we did was the goal was so we wanted to understand which is the best mechanism in order to perform the task that we have identified before. So we basically parameterized the mechanism, and then we formulated an optimization problem with Grasshopper and Tunni, and the outcome is a Pareto front that in our case the objective were to minimize the force and the velocity, which are two objectives that are opposite. And now what we are doing now is to identify which is the best mechanism for our use case. But then, since we started to investigate also the Revolut motor, we ported the same framework to the Revolut, and we are also in this case we are investigating the possibility of considering possible collision between motors. As you can see now in the figure, all the solutions that have red points, they are not feasible. Okay, this concludes the milestone. Let's quickly go to statistics. So this is the cumulative flow. So we have closed 88 issues, so 13 more or less issues per person. The release report, we managed to complete 62% of the open issue. And then this is the sprint burn down. I mean, the first and the last sprint, they don't make sense because they're not complete. Also, the first one was partial. And so let's just have a look at the 5 in the middle. So what we can see is that they are almost constant. Here we had a huge increase because there were some during the sprint I don't know, there was some deadline with the orders, so we rushed a bit while this one was Christmas holiday, and here where we started. And that's all for the ankle team. We move to the mechanical intelligence, which will be quite close. This is Technogym that is calling, and so mechanical intelligence, let's go quickly. So the mission is to investigate hardware optimization guided by data-driven and method-based technique. The team is composed by iRonCub, Delta, iFeel, DARWIN, and then there is the ankle. What I'm going to quickly present in these slides is not what we have done, but how we are approaching the problem. How we're approaching different problems with the same methodology. And the first one is the ankle. So basically what Alex is doing basically is that we have an optimizer that provides a population. The population is evaluated with a mathematical model, and then a simulation. Here, the thing is that what we are assuming that the design is not influencing the simulation, but is just influencing the conversion between torque to force. This instead is different of the approach that Punit is doing, because in his case the population is influencing the simulation and also the controller, so the pipeline is a bit different. While another approach that Shabarish is doing is basically here there is not an optimizer, there is Shabarish that is the mechanical engineer that is defining the population, also because here the design space was smaller. And so he created the population. Then with simulation, we have evaluated some possible solution in order to create a to understand which are the motion that are fundamental in order to create trust vectoring, and then we obtain the final design. And then a different approach that has been used for a different problem by Guglielmo, which was, so basically here we wanted to understand which was the correct mathematical model of the inverted roller screw. So what we did was we started manufacturing stuff, and we did some physical testing. Then with physical testing and a lot of analysis of YouTube videos, we understood that there was some problems, and then with some iteration we managed to obtain a final working design. And then just one word about other activity that we are doing in this team that are basically what also Giuseppe said before. We are also studying simulation, and these are the fundamental data in order to create this pipeline that we have seen before. And that's all.
Prova. So thank you, Fabio, for your presentation. Any question for Fabio?
Thanks a lot for the presentation. Let's say that I'm part of another team that I'm doing TSAD working simulation with the iRonCub. You did a lot of sim to real work. How can I use that?
Okay, basically, I think everything is committed, I hope. I mean, probably Carlotta can answer better than me, Carlotta and Roberto. How can you use it? I mean, we didn't do a huge analysis in order to gain tune the controller such that they have a comparable results. So we just we have an analysis in an experiment, then we did an analysis with simulation, with gain tuning, with the automatic gain tuning done by Carlotta, and then what I just noticed is that the results are comparable. Then the analysis probably needs to be completed. It's not a full analysis. We didn't tune the simulator. We just changing the controller managed to reduce a bit the Centurion gap. Then there is still you can also.
Yeah, let me only complement what Fabio just said. As Fabio said, we didn't actually tune the simulator per se. We actually perform an analysis comparing different kind of simulators in between Gazebo that has, I mean, every time we use iRonCub, we know which kind of issues we have, since we have a model just for Gazebo that increase inertias, Mujoko, and also about the time steps, which kind of time step was better in order to have a manageable simulation time, but still a symmetrical gap which is usable. And also we use what Fabio was saying, the automatic gain tuning, in which we perform a work. There is an open source repo on it, and there's also a publication in order to find the set of gains and the set of robot behaviors for the controller that ensure, to a certain extent, I mean, it was a trial and error approach, to be usable also on the real robot. And we use the same kind of automatic gain tuning infrastructure also for this project, even though in the future we aim to also tune the simulator in order to match real data, but for now we work more on controller, generally not in the lab.
Okay, time for question is over. We're already 5 minutes late. Thank you again, Fabio. Next presentation is from Osama for the iRonCub team.
Hey, the screen is shared. Good morning, everyone. Hosameldin. I'm going to, on behalf of the iRonCub team, I'm going to explain the planned versus the achieved milestones and discuss our plan for the what we have been doing in the last 3 months and what we are going to do. This is a quick overview. For most of you, it will be repetitive, but in case there are new incomers, this could be useful. So the goal of the iRonCub team is to equip robots with different locomotion types. We have usually robots that have terrestrial locomotion and other robots that have aerial locomotion. At some applications, usually we would like to have a bit of both. That's why we are trying to combine both capabilities in a single platform to have a multimodal locomotion capabilities in the robot. And this is where we come with our iRonCub, which is a humanoid robot equipped with jet engines to add the aerial locomotion capability in addition to the terrestrial locomotion, and also the manipulation capability that the humanoid robot usually has. The questions that we are trying to solve in iRonCub project is how to equip, how can a humanoid robot benefit from multimodal locomotion, and what are the challenges of the design and control that we are facing when we try to equip a humanoid robot with jet engines for multimodal locomotion. The developers team currently consists of 10 members. There is Antonello, who went for a period abroad in Stanford. And I'd like to take this occasion to give a special thanks to Gabri, because he has been around for many, many years. He has been leading the iRonCub team, and he has been giving us tremendous support. So thank you very much, Gabri, for being a very amazing Scrum Master. No, yes, thank you. It's not like goodbye. Yeah, so the team activities are ranging from experimentation to experimentation with the robot, with the jet engines, and trying to find models and simulation. And then it ranges from aerodynamics, hardware design and co-design, and also planning and control. Just to quick mention of dissemination, once again, kudos to Saverio for getting his paper accepted at ICRA. And also Anto's paper is under review, so let's hope for the best. For the PhD dissemination, there is Punis, who is going to have his second year review actually tomorrow, so good luck for him. Let's talk about the first milestones that are concerning the experiments, which is a group activity that every one of us is participating with. I'm showing on the right the bar that has the, I can point with the mouse, but anyways, it shows the number of open issues versus the number of closed issues versus the number of total issues. So you can see that most of our effort is in the experimental activities. We are also spending some time to clean up the software, and this time we have apologies. This time we have made a test with iRonCub MQ4 with jets on. So this has been the work that Shabarish has been developing, and we get to test it on the robot. You can see that we are putting some gloves to protect the hands from the heat, and on the right there is the footage from the thermal camera to understand where is usually what are the most affected spots in the robot. So this gave us good feedback for the next iterations. It's also good to know that our design can be attached to other robots. Our experiments in this iteration, we have conducted 7 iRonCub experiments given the time and weather constraints, and also 2 test bench experiments. Then let's talk about the base and jet estimation activity. That is mainly we are focusing on the jet engine models for estimating the thrust. as we found that it requires some attention because the thrust usually depends on the weather conditions. So if we perform an experiment in the summer and in the winter, we get different responses. So we had to have another iteration on the models. The base estimation algorithm is a task that is taken over by Alessandro. And the improvement, we wanted to have some ground truth. That's why we started working on using the setup that we have in the lab for giving the actual position to compare with our setup. The force torque sensor activities are more or less on hold this iteration because we are focusing mainly on the jet engine models. There is another interesting activity by Sandro that is we were trying to reduce the sim to real gap. So Alessandro was injecting the noise on that we have on the sensors to the simulation, and then Davide was testing with the controller. So in this way, we are closer to the real scenario, and we are identifying more or less closer behavior to the real robot. About the control, David is conducting his PhD, and he is basically advancing, or let's say, he's coming up with a new control architecture that he's going to present in the next presentation. So stay tuned. Just to give you a quick, okay, I'll try to be fast. Then there is Nicolas, who is conducting the nonlinear control activity that has been taken over after Fabio Bergonti was working on it. And he managed to build the Python bindings for testing in Python. I'll try to be fast. Saverio's activity was mentioned before for his master thesis work. At the moment, he's involved with the joint lab, so he's rarely having time to work with us. Hardware design is the activity of Shabarish. Thank you for Fabio for highlighting it. Basically, he's working on the thrust vectoring, and he came up with a conceptual design. So we are moving towards realizing this design into the real robot, and he's preparing also a publication for the thrust vectoring activity. The activity of Pony, thank you for Giuseppe for highlighting it. It's really nice that everyone is explaining the work before. So Punit, as Giuseppe was talking, he's expanding the parameterization that he did in the past for the whole robot. So he's considering more joints. And another activity that I wanted to highlight is he has been working with Mujoko Simulator. He ported the iRonCub controller into Mujoko Simulator to be able to test his pipeline, but for now his focus is back to the reinforcement learning environment that Giuseppe developed because it would give more promising results. The activity of Anto, thank you Giuseppe for explaining it before. You made my job very easy. Basically, yeah, he's exploring more physics-informed neural network models for his aerodynamic modeling. Just a quick mention of the statistics. Basically, we moved to GitHub project, so we didn't really start immediately from the beginning of the iteration. That's why you can see that the issues started being closed from the beginning of December. But at the end, the issues closed somehow looked comparable to the previous research increment. This is an interesting one, can show where is most of our effort lies, and usually it's in the experimentation. So these are the labels of the GitHub issues. So the GitHub issues with label experiment have high effort, and also the ones with label implementation, which makes sense. Management, yeah, because so many purchase issues and other management tasks that that we are doing. Other than that, thank you very much for your attention.
Let's thank Osam. Any super quick questions? We are 2 minutes late. We gained 3 minutes. Thanks, Osam. Okay, if no question, let's go with the next presentation from Davide Gorbani. We'll talk about MPC for the iRonCub.
Okay, so hello everyone. This is the iRonCub vertical presentation, and today I'm going to talk about the integration of an online linear MPC with an instantaneous body controller for the iRonCub flight controller. So first of all, I would like to give you a brief overview of the iRonCub software architecture. So first of all, we have here the base pose estimator, which retrieves data from the iRonCub sensor, which are in IMU and real sense, and estimate the base position. Then we have the JAXsim device, which is devoted to the communication with the jets and to the estimation of the thrust. And then we have the flight controller here, which compute the desired thrust that is sent to the JetCat device, which will then compute the throttle to send to the jets, and the desired jump position, which are directly sent to the robot. So our flight controller is a momentum-based flight controller, meaning that we exploit the momentum equation. Here we have the equation of the momentum derivative. The first term here account for the force produced by the jets. The second term is account for the contact forces, and the third one represent the gravitational force. In our case, we neglect the contact forces because we don't have an accurate estimation, and we introduce this parameter that we call alpha gravity, and this is introduced to deal with the takeoff phase. So the alpha gravity is 0 when the thrust of the jets is in idle, and is 1 when the robot performs the takeoff. In our controller, we use the momentum equation in body coordinates. So we start from the momentum equation in inertial, and we linear and angular, and we pre-multiply by the rotation from inertial to body to bring it in body coordinate. We derive this equation to get the equation of the momentum derivative in body coordinate. And as you can see here, there is this term, which is the momentum derivative in inertial that we saw in the previous slide. And here we have another term, which is a bias term. So at the end, the equation rewrites like this. The problem here, so we write it in body because in the doing that, we have that the A matrix depend only on the joint position. But here the problem is that this equation is nonlinear in joint position and thrust, as you can see. So what we decided to do is take this term and linearize it around the current joint position and thrust. So this is the first order linearization of this term. And as you can see, the first partial derivative, basically the A matrix computed in S0, while the second one, we call it lambda matrix. And then, as you can see here, if we rewrite the whole momentum derivative equation, becomes like this, and this is linear in the variation of thrust and jump position. So the first controller that we came up with is an instantaneous body controller that run at 1 kHz and compute the desired thrust and the desired joint position. This is the formulation of the KPI, so we chose as control input the variation of joint position and thrust, And then in the cost function, we have the linear momentum task, which basically is needed for controlling the position of the robot. The angular momentum task, which is needed for the orientation of the robot. And then we have a postural task to keep the control input as low as possible. And then this is subject to the following constraint on the maximum variation on joint position and thrust, and maximum and minimum thrust and joint position. However, this full body controller has a limitation. The main limitation is that the jets have a slow dynamics. So when we set a reference in thrust, this cannot be really well tracked. As you can see here, this is data from a test-bench experiment. In yellow, you see the reference thrust, while in red, the estimated thrust, and blue, the measured thrust from the load cell. And as you can see, the estimated thrust show a delay with respect to the reference thrust. And here is the data from a real experiment and the video of a real experiment. Also, here you can see this is the desired and estimated thrust of one of the 4 turbines. And as you can see, the robot is able to take off, but then soon after it loses the control of the orientation. So in order to address this issue, we decided to add on top of the instantaneous full body controller a linear MPC. This linear MPC runs at 10 Hz because it's the same frequency as the jets run. And so if we would run faster, all the throttle command would be lost and not actuated. And the main peculiarity of this MPC is that compute directly a throttle reference for the jet, and not a thrust reference. And then the MPC also give a joint position reference for the instantaneous controller, which in this case compute only joint position to be set to the robot. So here is how we decided to implement the MPC. In this state, we have the position of the center of mass, the linear momentum, the roll PQ of the base, the angular momentum, thrust and thrust derivative, while our control input are the variation of joint position and throttle. And as you can see now, the thrust became a state and no more a control input. So we chose as a dynamical model the following. So the first and third line basically are the equation of the linear and angular momentum. The second and fourth rows are the basically the equation of the momentum derivative that I showed you before, the linearized one. And then we have the model, a second order model to characterize the thrust. And as you can see, depend on the thrust derivative and the throttle. And this is linear in the throttle. So also this MPC is linear in the control input. And here is how we selected the cost of this MPC. So here we have first the cost related to the tracking of the reference state. And then we also have a postural task to keep the control input as low as possible. And then as a constraint, we have the usual propagation of the dynamics of the states. And then we have some constraint on the control input. Instead, the whole body controller, we modified it as follows. So we chose as control input only the variation of joint position. And then in the cost function, we have this term here, which is a postural task, which keeps the joint position as close as possible to the reference coming from the MPC. And then we have the following constraint on the variation of joint position. So now I'm going to show some simulation result, and the first one is here. This is the simulation performing gazebo, and here we are also simulating the jet dynamics. And as you can see, the robot is able to follow a predefined trajectory, both in position and in orientation.
3 minutes left. Sorry.
What? In this video, we see that the robot is also able to recover from an external disturbance. While here we have the result of the latest test on the robot, and thanks to Bruno, we have a 4K video. And now, as you can see, the robot is still able to perform the takeoff. It managed to kind of hover for 1 second, but then again the robot fell. And the current limitation that we found out is basically first one, the sim to real gap. We can basically sum up the limitation in this one, but in detail we have that the jet model that the MPC uses strongly depend on the air condition, and this is not as very easy to model. Then in the MPC, the state or the thrust and thrust derivative is not updated with the estimated thrust, but the prediction of the MPC at the previous timestamp. And then we found out that there are some delays in the communication with the turbine. So when we actuate the throttle, it takes few almost half a second to be then properly set in the jets. And we are working on in future improvements. So the first one is to improve the simulation and add maybe some disturbance in the jet forces in gazebo. And then I'm also working on in the Cascade MPC. This is mainly to overcome the issue of running the MPC at 10 Hz because of the jets running at 10 Hz. So I'm thinking about adding a second linear MPC. In this case, this will not compute a throttle, but the thrust will be only the measure one. And this will run faster because we know that we can set the joint position desired at a higher frequency. So this concludes the presentation. Thank you for your attention.
Thank you, Davide. Any question for him? Okay, Dani.
So the idea would be to add another layer of MPC where we keep the throttle constant, or what is that?
Here, the MPC, the control input will be only the joint position, so it will get the thrust from.
Okay. We cannot make the other MPC faster.
We cannot. I mean, why I thought about this is that this first MPC has to run at 10 Hz because then the jets have the inside control loop that run at 10 Hz, so it doesn't really make sense to have a.
I understand, but you can put in the constraints of the MPC that you generate, let's say, so you have the throttle, and then you have different frequencies of generation of the thrust inputs. No, I'm looking also the MPC guys that are faking to be busy. So no, I'm asking. So we can. We can keep the discussion offline. I don't want to polarize that, but yeah, okay. Thank you.
Okay. So next presenter is Giulio Romualdi for the Delta team. Let's welcome Giulio.
Okay, so let's start. This is the, let's say, the update for the Delta team. So the Delta team is one of the team of the ErgoHub team. That is a huge team that contains the iFeel team, the human team, the Delta, and then the newborn ankle team. Let's say the main mission of the ErgoHub team is the application of ambient intelligence and collaborative robotics for risk prevention in work environment. And so in the end, to solve this problem, we have, say, the wearables, in which the iFeel and the human team are, let's say, the main responsible, and then the robot, where, let's say, the robot that we already have, that is the ErgoHub robot, the Delta team is the, let's say, the main responsible for this part. So where we are now, we have this, the classical view that I show you. I had some other clips where we have the robot walking and seeing that, I mean, it's not so robust, even if we are able to show some demos here and there. So this is actually where we are today. So today we have a robot that is able to walk in position control, and this is actually let's say, a limitation of our control infrastructure. The fact that it's in position control makes complex the interaction with the environment and the, let's say, the humans, for instance. So let's say our goal, our moonshot is having something like this. Okay, Fabio already showed this video, so you already seen this video. This is the Unitary robot. So you may think, okay, but this robot is completely different from ErgoCub. ErgoCub is taller, and the weight of this robot is less. That's true. But in the meantime, there is also the Tesla Optimus robot that is similar to our for the size, let's say, and for the weight, but is able to do crazy stuff, at least for us, like walking on uneven and rough terrains and able to recover this kind of. So let's say our goal is to have something like this. So in the end, the Delta team mission is to design a robust, reactive, and dynamic architecture for, let's say, locomotion and human-robot interaction. In the end. This is the classical slide that I copy from one research increment to the other one. So in the end, we have several actors. Some of them are in other teams, some of them are mainly working on the team, but in the end, here we have Giovanni, Roberto, Evelyn, Carlos, Lorenzo, Mohamed, Ines, Filippo, Guglielmo, and me. So let's go to the, let's say, to the team objectives. So we have several team objectives. The first one was to have a momentum-based balancing controller up and running on ErgoCub, working with the UKF and the friction compensation that Ines developed during her PhD. So this objective has been completed, and this is the video. So this actually is one of the video that Ines will present to her PhD defense, where we have two ErgoCubs working with the, let's say, same controller, and let's say the low level is different from the one that we used to have, that is the wall biodynamics, but is let's say a UKF filter that considers also the current measurement. Another task was to bring the robot to humanoids. Okay, this is, let's say, has been completed. This is one of the pictures of that Bruno actually took during the event. There was another task that was try to make the robot walk where the joints are controlling velocity. This is an activity that is, let's say, slowly starting. This is a collaboration between tech and us, actually with Carlotta and me, where we, let's say, move our analysis from the robot to the test bench that they have, since we found some, let's say, modification that has to be done in the firmware. So testing it in the test bench was easier. Another important task was to investigate possible solution for, let's say, modeling motors plus gearbox. This, let's say, it's a step towards having a better torque control. These are activity that is ongoing, and then actually with the help of Giuseppe and Fabio, we decide a list of possible experiments that we can do with that. Hopefully, test bench that will arrive at a certain point of our life. And so now the idea is to try to say convert these experiments to real objects. So in order to do these experiments, we need this object, and then open a boom and decide to how to buy and how to man the stuff. Okay, then there were some, let's say, more personal objectives. So for the low level, Ines was able to implement UKF for floating based on ErgoCub. I'm not going to show you again the video because it's the video that I showed you before. Regarding the base estimator, actually Guglielmo worked a lot in the ankle team. So these two tasks, that was having the base estimator up and running on the robot, and then extract planar feature to, let's say, to generate full steps, has been delayed. On the other hand, regarding the FT calibration, Filippo investigated a lot on the effect of the temperature, as already Giuseppe mentioned this morning, and he validated the training model on the ergo leg. So this is actually the plot that Giuseppe showed this morning, but this is the effect of this there is related to the temperature, and then on the left, and on the right you can see the, let's say, the output of the neural network is able to partially mitigate this effect. Okay, so regarding model-based trajectory control, last time there was to define with Mohamed because Mohamed wasn't here. So then Mohamed worked a lot also on the Honda project, and we are currently working with tech on the new mobile base. So there is an activity ongoing. Oops, this is the video. Tranquillo. Okay. Tranquillo. So there is the video where I'm trying to collect some data to analyze the reachability space of the current ErgoCub. So there are for sure more proper ways to analyze the reachability space. This one was the fastest one in order to give fast results to the iCap tech team. And then, okay, there was the work of Lorenzo. It was actually, I'm not going to talk a lot about this because Lorenzo will do the vertical presentation after me, but he was able to port the momentum base. That is actually the video that I showed you before. So let's say for the high-level controller was mainly Lorenzo in charge of the task, while for the, let's say, connection and low-level and identification was Ines. Okay, regarding the data-driven, there was the reinforcement learning. There was the task was trying to port the MPRL on ErgoCub. We did some experiments on the robot. It's not working fine, as you can see, but at least it's not exploding. I mean, at the beginning, the first experiments that we did, the robot was not able to do nothing. We were starting the policy, and then the robot was doing crazy motion, then fixing bug here and there, adding some randomization, we were able to obtain this. Still, there is a lot of stuff that we have to do. Okay, then trajectory generation. So Evelyn was able to implement the, was working on implementing the first prototype of, let's say, data-driven approach for collaborative caring. So this is, let's say, on the right, you can see one of the data collection, let's say, campaign where there was Evelyn and Mohamed. One of the two was the human and the other one was the robot. That then this data will be considered in a, let's say, neural network, let's say, man fashion. So similar to the work that she did during the, let's say, the first year of her PhD. And the idea is to, let's say, automatically generate trajectory that will make the robot follow the human while moving an object. Then she's, let's say, paused this activity because then she left to Manchester. So she was able to perform a literature review for the project, and actually she will work on the Koopman operator for, let's say, linearized, non-linear system and improve in theory, control, and plumbing. So she's started from toy problems because it's a topic that was a bit away, far from what she was doing before. So she started from a toy problem that is a classical damper spring mass system. where there is a neural network that should try to, even if this system is already linear, but it's try to, let's say, find a new representation for the system. That should be simpler to control. Okay, then last time we had let's say, we had these two milestones here, but then the work of Carlos and Giovanni has been, let's say, moved on the X team. So I put it here because last time we put it there, but so the activity has been carried on by Stefano. So regarding the trajectory generation on the model base, Roberto was able to perform and complete the experiment campaign on the ErgoCub that allows the, let's say, the robot to walk on the, let's say, inclined plane. In this experiment here, Roberto was, let's say, just play the trajectory, play the joint trajectory that the trajectory optimization were generated. So let's say, at least these campaigns concluded. And then the idea was trying to, let's say, consider this whole body trajectory generated in a closed loop fashion, but this has been, let's say, stopped for the time being. Okay, there was another task that is switched from Zenab to GitHub project. It has been done, as you will see later on the plots. Regarding the dissemination, Ines submitted her PhD thesis, and she also submitted a paper, a RAL paper on the, let's say, UKF and friction compensation. And this is actually the, let's say, the submission. Actually, okay, I didn't put it here, but also the paper of Mohamed has been accepted to RAL. But Daniele already mentioned this. Then regarding Roberto and Evelyn, the plan was to resubmit for Roberto the RAL paper, but this has been, let's say, delayed for the time being, and he will focus on this on the next, I mean, the research is increment starting from tomorrow. And then the same for Evelyn, because she worked on other tasks, and in the end we decide to revise and resubmit the PI DRM paper in IROS that will be in these 3 months. So some numbers. Okay, yeah, so it's not super easy to compare a GitHub project to Zenab. So I would say that the most important part is one of the most important parts. So more or less the number of issues closed by each, let's say, individual is similar. Last time we closed 14 issues, this time is 10, so 4 issues less. Okay. The statistic burn down, so the close issue sprints. You may wonder what is the 2004 and 2005. Well, it was Christmas and then it was a Happy New Year, and that one was the period. And then there was another, let's say, plateau that was the humanoids, in which part of the team was there. But I would say more or less the trend, except for Christmas, that is normal. That of course people have to rest, but let's say the trend is constant. So that's it.
Giulio, any question for him? Dani.
Thank you very much, Giulio. So, concerning the torque-based reinforcement learning, so how do you see that thing happening in the
one that we saw, that the policy generates
directly torques or currents?
So I have to tell you the truth. I think that now in the team we have to try to, let's say, to close the part related to the low level and attach it to what we have, and the something related to the base estimation. And since the people
good.
So then it depends
it's a
on
problem in the future. Okay, good.
Other questions? Okay, in this case, next presenter is Lorenzo Moretti. Let's welcome also Lorenzo, vertical presentation for the Delta team. You only start with the 1 minute penalty.
Okay, thank you. Okay, so hello everyone. Today we'll talk about momentum-based torque control for balancing and walking of humanoid robots. So first of all, I would like to explain why we revive a model-based control in an age where robotics is pushing a lot towards data-driven control policies. And the main reason is because our ultimate goal is torque control walking, as Giulio mentioned before. But torque control is not trivial, especially when trying to execute a trajectory. And this comes particularly true in case we are working with the humanoid robots without torque sensors and with high reduction ratios, such as iRonCub. These reduction ratios can cause this high friction that we need to compensate. And for this reason, we chose to start working at a high level with a simple controller in order to not add more complexity. And in other words, we want to have something that was as simple as possible, but not simple, as a famous scientist was used to say. And now I would like to give a quick overview of the mathematical models we are using in this controller. So as per the name of the controller, we start from the dynamics of the centroidal momentum, from which we can easily get the contact forces that allow us to track a certain reference for the centroidal momentum. And on the other side, we can write the full equations of motion of the full robot. And if we combine them with the holonomic constraints at the contacts, we can rearrange them in order to get the joint torques. And in this equation on the right-hand side, you can see that appears the term of the contact forces that we can substitute from the equation we got above. And lastly, we can leverage the null spaces to to try to accomplish further tasks. For example, in the equation above, we can set through the null space a torque minimization task, while on the second equation, we can try to set a postural task. And with that said, we can get at the end the joint torques with other control command that we send to the low-level controller. And this is exactly the control architecture. So we have this momentum-based torque controller that is sending the joint torques to the low level. And if we are talking about a balancing action, we have a simple offline planner that is providing a sinusoidal trajectory for the center of mass position, for example, in the y direction. And then we tried to put this on the robot. This is the video that Giulio shared before. So at the high level, we have the momentum-based torque controller, while at the low level, we have the work done by Ines with UKF and the RDE. And you can get this torque control because the robot is not stiff. It is pretty compliant. Ines can interact with it. And given also the energy Ines is using when shaking the robot, this means that the whole control architecture, also high level and low level, is pretty robust to external disturbance. So at this point, we thought, how can we extend this control architecture to walking? And the first pretty simple idea was, okay, we do have a pretty good whole body position control pipeline for walking. Why we can't recycle some of the ingredients of this architecture? And among these ingredients, you might recognize the unicycle planner, the COM-ZMP controller, and the copy inverse kinematics. And this is indeed what we have done. So on the right-hand side of the control architecture, nothing changes. But now instead of the simple offline planner, we have a more advanced online planner that consists of the unicycle planner that plans the steps, the COM-ZMP controller, which stabilizes the COM trajectory, and the copy inverse kinematics that provides then the reference for the whole body motion. So this online planner is providing to the momentum-based controller the references both in the centroidal, so the centroidal momentum, but also for the postural tasks, so the joints position and velocities, as well as the contact status information for the feet. As usual, we first test our controller in simulation to not break the robot, and this will happen. So the robot manages to walk, but it is a kind of shaky and bumpy walking with the swing foot not performing a smooth trajectory from one step to the following one. And since we changed a lot the planner, it can happen that with the model-based control, you need to retune stuff. So we thought that this was a problem of, we were confident about the architecture, so we thought that this was a problem of retuning gains, but we didn't feel like to do it manually. And for this reason, we leverage the Python library called PyGuard, and that deploys, that implements a genetic algorithm. In our lab, we are we have a lot of experience with it. Think, for example, the work of Carlotta or Fabio. Here there is nothing fancy, but what is interesting is that we didn't want to rewrite the software stack. We wanted to use the exact same software stack both in simulation and in on the robot. So for this reason, within the step of calculating the fitness function, you might recognize that we are running the exact same commands we run or in Gazebo or in the robot. So the advantage of this pipeline is that the software stack in simulation and production is exactly the same. So the software being optimized is exactly the same that is going to be simulated or deployed on the robot. And but there is no free lunch, so for sure there is a disadvantage. And in our case, as far as we know, we cannot parallelize this process. So the tuning is a bit slow. Nevertheless, we managed to get pretty good gains, and in fact now you see the simulation is a lot better. The walking seems pretty fine, and the swing foot is now performing a pretty smooth trajectory from one footstep to the following one. So since we were kind of happy with these results, we decided to go to the robot, and this is what we got. Yeah, so unfortunately is not working, but if we watch it again, you see that at least at the beginning the robot is performing the right movement. So it's forced move the weights on his left foot, and it tries to lift up the right foot to perform the fourth step, but it doesn't manage. And this opens to our future directions. So first of all, we would like to start with a simpler trajectory, such as this one, step-in-place trajectory produced by a more advanced planner, which is the one done by Roberto. And you can see this trajectory is a kind of interpolation between a balancing motion and a walking forward motion. And secondly, as also anticipated by Giulio when answering to the previous questions, we would like to invest a bit of time to improve our base estimation pipeline, since this will be extremely important, but we will, at a certain point, be able to perform the 4 steps. Thank you for your attention, and I guess I save up this 1 minute penalty.
Yeah, we are 5 minutes early, so now we have a 5 minutes question for Lorenzo.
Thanks a lot for the presentation. I have 2 questions. Which model are you using in Gazebo, and which value do you use for the cutoff filters that are in the input and output of all body dynamics? And did you consider changing one or the other?
So for the Gazebo, we are using iRonCub Gazebo V1_1. And the second question was about the filter cutoff frequency. So in the case of the balancing, we are not using dynamics because it has a low level and also as the perception pipeline, we're using the inner stuff. For the walking, we didn't manage to connect Ines work to the high-level controller, so maybe things will automatically improve. And we didn't change the cutoff frequencies from the default, which I honestly don't recall is 100 Hertz. 3. Ok, so ok.
No, Silvio, l'abbiamo cambiati una volta. Cambiava niente.
Okay. Yeah. Okay. But also in the second experiment, the walking, we are not currently closing the low level. So we are the KP of the torque control is are set to 0 because we tried to increase it a bit and the robot was exploding. So I don't know if.
Yes, but the gain tuning was done with the completely crazy inertia. So probably the gains are optimized for crazy inertia, not for real ones. That's it could be that they don't change a lot, but really,
makes sense.
I really regret naming that model gazebo. We should actually, why can't we do it? Let's rename it iRonCub with the really crazy big inertia. Don't use instead of because it's really because it really doesn't make any sense. You cannot use it with the. It depends on the integration step you are using. With which physics engine did you try it? Sorry, Giulio said that in the past he tried, but he tried with a maximal coordinate physics engine that is integrating 6 degrees of freedom for each body, that is introducing much more numerical noise. So I don't know what the trade-off is with the with the Dart, that is a minimal coordinate engine with gazebo. But anyhow, the point is that the model being named gazebo doesn't convey all this trade-off. That is true. That is true. It's true. Is if you want faster, the fact that there is a model called gazebo doesn't convey all this information to the user in an easy way. And that's my fault. I named the model, by the way. And it's not that I'm scolding anyone, but I think it's important to understand that we have these models, one with really crazy inertia that can go faster, the other that is the proper one. You can use it. The simulation needs to go slower because of numerical issues. How much slower it depends on the type of physics engine that you are using, and that's also for if you are using JAXsim or JAXsim, whatever. There is always this trade-off. Okay, thanks. But I really suggest trying to modify it because those inertia are really crazy. Thanks.
Okay, so thank you for the presentation. Actually, mine is a comment more than a question. So regarding the base estimator, I think that the tricky part that we have when we use torque control instead of position control is the switching of distance foot. Because in position control, historically also this one is my fault of years ago, but it's like this. So historically we switch from this distance foot from the left to the right or the opposite just 1 instant before lifting the foot. And this is more or less fine in position control because the foot remains there, but then in torque, when you are in torque control, in general, the foot that is going to be lifted will slide, and so this will mess up the completely base. So more than just base estimation, I would say also decide which one is the master in the foot, master foot, and so on. That is in the umbrella of the base estimation.
Yeah, makes sense.
Other questions for Lorenzo? Okay, in this case, we have half an hour break now. We will come back at 11:30 with the presentation of Team X. Welcome back. We are resuming after the break with the presentation of Team X by Stefano Dafarra. Let's welcome Stefano on the stage.
Thanks a lot, Guglielmo. So I'll directly start with the goal of Team X. So Team X has a goal to create new robotic demonstrations that highlight the capabilities of our humanoid robots. I've showed this video also during the past research increment, but I thought to keep it. It is a sort of a slideshow of the demos since 10 years, basically, when we started from basic interactions to the robot balancing on stage, and also balancing and walking during, say, during particular shows, like in that case was a Dolce & Gabbana shows. We moved forward considering also the capability of recovering from pushes on the arms, and then teleoperation. Here is the work carried on by Mohamed in his first period in the lab. The teleoperation has been quite an experience for us, and has been a great source of a great investment of some time that led us to having an avatar system that used the iCar3 robot for the X-Prize competition, involving different type of capabilities. Moving from iCar3, we arrived to iRonCub, where we managed to port basically most of the capabilities that we had on the on iCar3, from walking to through teleoperation, with the aim of performing in more industrial setting, like here, like in a warehouse. And this is going to be fundamental also for the future research increments. Indeed, the manipulation capabilities needs to be central in order to give added value to the robot. Not only through the use of teleoperation, we managed also to take a step further and trying to remove the operator from the loop and having the robot autonomous. So the teleoperation data allowed us to train neural networks that are able to replicate the motion of the operator under the same circumstances, under the same type of inputs. And this is the work of Carlos here with the robot walking autonomously in the lab and carrying on objects when prompted to do. So this is a sort of the storyline of the past, was probably 10 years of demos that we had with the robot cutting a bit of corners. So what's next? What we try to achieve now is to point the robot to an object, and the robot has to reach it and grasp it. So as simple as that. The people behind the team are the following here. In particular, I think that this research increment has been a bit of it has been of a transition, let's say, because also at the beginning of the research increment, two people from Pavis, in particular Matteo Tiezzi and Tommaso Picella, joined, let's say, full-time on the team. They are completely part of the team activities, and I'm pretty happy with it. So I'm happy that we're also collaborating with other teams within IIT. During the past research increment, we only had in the end one big demo, which was Humanoid in Nancy between 20 and 22 of November, where we brought in the end a true robot plus iRonCub. So we had 3 robots there running. We had all sorts of issues, and it was definitely a complex task, but again, it was quite an experience, and we had the robot performing autonomously on stage in front of the Humanoids audience, which is made of, say, our colleagues, and the results were still impressive. So I'm pretty happy about the result. Going straight into the milestones that we set last time and going one square at a time. Starting from the first, we wanted to investigate alternatives, alternative architectures for XPG, exploiting transformers. So this was this indeed is the reminder of the video that Giuseppe showed before, with the robot using a transformer instead of the classical STM for the learning part. And we noticed that it was kind of able to match most of the capabilities of the old architecture, although it's still not perfect. For example, it was dropping the box. The walking part was quite good, although it was able only to turn right for some reason. So he was pretty good in following Carlos while going right, while on left he was kind of refusing. Said it was just trying to go forward or right. But it was quite precise in following and stopping when needed. Interestingly, this was the first checkpoint of 5, and all the laters were working worse. So it means that he's overfitting a lot, and there's also still a lot of space of improvement. Then we wanted to add more inputs to XBG, and this is an activity that we just restarted this week. And we wanted to add more action to XBG, practical and social regarding social interaction. We did have a first test on Tuesday, and we'll have another test on Thursday, but we are mostly there. Then we wanted to improve the experience of the user experience of the LLM part of the autonomy. This is something that we keep iterating, also considering the recent demos. And it's still ongoing. We are trying to conclude it during these weeks with Giovanni. And Giovanni also wrote a paper regarding the infrastructure of the LLM plus XBG, and we need to submit it, but is ready to go. For the third of 4 rectangles, then we wanted to take more data for manipulation task, and something that we did, and we are trying to exploit. We still haven't ported on the robot yet, the results. Instead, we sort of postponed the investigation language conditioning for manipulation task. It is something that we still have to properly delve into. Then we also investigate how to integrate walking with scene understanding. And this is the...
Can you walk to the man with the tablet?
This is the result. So there is Carlos speaking behind, but it's actually me typing on the keyboard because we are still integrating it. Here we're using Gemini.
Can you do what is written on the tablet?
And the interesting part is that it's pretty smart. So in the first part, I was just telling to reach the person with the tablet, and the second part, I just typed to do what it was written on the tablet. So it was not just able to, it was able to recognize what it was written, although it was flipped upside down. It was also able to walk. So I think this is quite impressive, and it opens up a lot of routes of exploration with this type of model, which is we just came out on December. But the integration with it has been quite straightforward, and we do hope to use it more in the coming weeks. Finally, we still have to understand how to have feedback from failed grasping, but also the advent of these new, more interesting, more capable visual language models can also help us in that. We do have also architecture improvement with these are milestones with the Pavis, with Tommaso and Matteo, and we are adding an evaluation block on the output of XBG and investigating continuous learning. It is something that we are actively working on, and this is important because as I said before, these models tend to overfit a lot, and this will be a way for detecting when we are overfitting and avoid to forget past capabilities once we try to add new actions. So this will be fundamental. As I mentioned, this research increment was also a sort of a transition moment, which basically meant try to integrate and work a lot on the code. It is the PR that has kept involved the development, the dev team for most of the 3 months. The numbers are huge, but this actually is just an integration PR, and everything was already merged before. But this was just to say that during this month we did spend a lot of time in improving the code, trying to make it scalable, trying to run it run it also on the external infrastructure like Franklin and other high performance computing clusters, let's say. So this was a necessary activity that took a lot of time. Statistics. For the amount of closed issues, we didn't close a lot. We had in around 48. We still have around 91. We opened a total of 91 issues. These are the issues per sprint, the open and closed ones. During this sprint, during this increment, I did not pass through sprint the issues. So the first one is the one that we did all the inherited issues, and they remain there. So that's why they are it's so tall. Instead, the later ones are with the 2 weeks after we didn't open anything new. And then we started opening again, starting from the 3rd and from the 6th. These are also the issues per label. So we did focus a lot on implementation. We still have a lot to do, but we did close a lot of implementation, and also experiments and announcements is where, let's say, the main activities during the past research increment. This concludes the presentation. I believe I'm a little bit in advance. Happy to receive any comments or questions.
Let's thank Stefano again. And any question for him? From Silvio.
I guess everybody's that is checking any kind of news is aware of the new DeepSeek models. I saw that they also released something related to VLM. Did you already check if they are comparable with what Gemini is offering, or I don't know?
There is one thing we did check with the well, actually, Giovanni also mentioned that to me, and in principle we could try to use it. It's available also for offline usage, which is pretty cool. There is one key feature that Gemini introduced with the latest release that we did exploit in the video before, that is the capabilities of automatically segmenting the images. And so Gemini is able to output a JSON list with the items that are in the picture with the bounding boxes. And this is something that I've only seen in Gemini so far. There are possibly other models, but I haven't seen it. I checked quickly and I didn't notice a similar thing for DeepSeek. But on the other end, is also we are trying to remain as transparent as possible with respect to the LLM, and I do hope that in the next couple of months there will be a ton more models that are going to work better, faster, and so I'm looking forward to integrate them.
Other questions for Stefano from Gianluca?
Thanks for the presentation, Ste. My question is about the goal. You said to point the object, and he has to understand that he has to grab it and bring to you. If as a next step also you would consider also the possibility to map the environment, the robot arena in this case, or
this is a pretty good question, and the point is that initially we did thought of starting from creating a map and then try to act on that. The point was that in any case you first need to have a map, right? And so you can just expect to bring the robot into a new room and wait. This is an alternative path eventually. I also think that given how good the LLMs are becoming in understanding what is around, you might not need necessarily a map beforehand, but you could construct it. So yeah, I do agree that for future developments we might consider looking, keep tracking of what we've seen around, what the robot was able to notice, and then so that if I asked you to grab something that was behind your back, you're still able to understand that it's there. But so far, I was just thinking, okay, to tell the robot to do something according to what it's currently seeing, and if it's not seeing, I will just tell him to turn. So this was the initial plan.
Another question from Dario.
Actually, I was to one thing to Gianluca about this. Yesterday you were busy, but a guy from HSP is actually doing that.
Exactly.
Actually using LiDAR to map and navigating to an object.
Yeah.
That.
I know that they are tackling similar issues, and but we are just attacking from different point of views, let's say. So.
Okay, if there are no other questions, let's thank again Stefano. And let's welcome on stage Ilona with her presentation on social implication of teleoperation. Thank you, Ilona.
Good morning, everyone. Thank you for inviting me to the 20th research increment. Today, I will do a presentation with the title Exploring the Social Potential of Teleoperation, Object Manipulation, Subjective Sensations, and Full Body Illusions in Human-Robot Interaction. I would like to introduce you to my research of the past few months here at IIT, which is dealing with the question, what happens when humans teleoperate a robot as a second external body? My perspective on this topic is rooted in human-robot interaction studies and social sciences, and it addresses the practical and subjective aspects of teleoperation experiences. Just a second, I lost my cursor, which I need. Okay. To find answers to my question, I did a long-term study with 8 to 10 sessions and 7 participants as teleoperators. In this presentation, I would like to introduce to you the 3 key areas of these experimental sessions. The first area was exploring ways of object manipulation, to find the range of motoric skills and limits of controlling the robot. The second area is exploring phenomenal or subjective sensations of users while controlling the robot. And the third area is investigating body illusion studies. So while I introduce each study, I will present some videos to illustrate my assumptions. Okay, let's dive into the first part, which addresses object manipulation. I was looking for the limits and the range of skills of the participants' motor actions in controlling the robot while they were doing object manipulations over an extended period of time. The manipulations consisted of training the placement of objects like a bottle, a box, or a cup, into various spots, so from here to there. And additionally, participants practiced actions like drawing, unfolding boxes, and throwing a stuffed toy. The preliminary results show that controlling a humanoid robot requires the teleoperators to develop a new set of skills for adaptation to the robot's physical structure and motoric capabilities. As outcome, an increase in precision, in speed, and in overall body control, along with the unfolding of flexible and creative handling of the objects, was observable. This means the ability to lift, grasp, or reposition objects became more versatile over time. Furthermore, there was an improvement of handling the environmental space, the distances, and the depth estimation. But controlling the robot also showed some limitations. For example, the robot struggled with tasks requiring fine mechanical precision or force modulation. On the hardware side, limitations occurred with easily breakable, fragile hands, or the overheating of motors or sensors. Also, the low resolution of the headset caused tiredness and difficulties in depth estimation for the teleoperators. Furthermore, the users often demanded tactile feedback, which could serve as possible help for lifting, touching, and force control. But overall, it turns out that it's beneficial to practice and train the manipulation of objects over an extended time, and that skills in grasping, estimation of depth, as well as the versatility of using the robot's body, improve significantly over time. For training, it seemed helpful to have a partner to interact with the robot, to help guide the robot's actions, and to help regulate the force control that prevents the robot from colliding with its own body or its surroundings. Okay, let's move to the second part, which addresses the teleoperator's subjective experiences of selfhood or being present in the robot's body. But maybe we watch another throw. Could have been, yes, quite far. During the experimental sessions, I constantly asked the participants while they were controlling the robot questions such as, where are you right now? Or can you tell me who you are right now? Or can you feel my presence? Can you feel my touch? The aim was to explore the subjective experience of perceiving the robot as an external body. Participants described a wide range of experiences. Some felt the robot became an extension of their own body, while others described it as replacing their original body. Some participants also reported feeling the presence of the interaction partner, or they described emotional engagement during human-robot interactions. So there's a potential of teleoperation to create meaningful connections and agency in social contexts. These findings have an impact on applications of teleoperated robots where social interaction is key, such as fields like remote collaboration, therapy, and telepresence in hazardous environments. Another focus was to investigate how controlling a humanoid robot affects self-localization and body ownership. So we looked for ways to increase the convergence between the human body and the second robotic body. Finally, we conducted 3 kinds of experiments that induced different body illusions for the teleoperators. First, we investigated full body or upper body illusions, of which you can say they are similar to the well-known rubber hand illusion. For this, we performed tasks in which we touched the upper body parts, both of the robot and the teleoperator, first synchronously, so at the same time, and then asynchronously with delayed touch. This resulted in participants experiencing a fusion of their sense of body ownership with the robot's body and perceptions. The synchronous touch shifted the subjective sense of being present into the robot's body, even though the body awareness remained tied to the teleoperator's physical body. With asynchronous touch, in some cases, a moment of pre-reflexive sensation was observed, where the controllers expected to feel being touched, but the sensation of tactile feedback remained unfulfilled. Next, we introduced mirror illusions, which enabled participants to effectively see the robot's movements in a mirror. This allowed the teleoperators to switch from the first-person perspective to the third-person perspective while controlling the robot. The setup facilitated the creation of a body scheme for the robot's body and improved the participants' ability to assign postures, distances, and ranges of motions to the robot. And maybe it also created a kind of muscle memory, because after these sessions, the controller's body awareness for the robot body improved, as did the ability to estimate the body position for further actions. For example, they used less force in their following actions, and they were aware of their body range of motions, resulting in fewer collisions of arms, fingers, or hands with the robot's body or external objects. And finally, we explored out-of-body experiences using a setup where participants stood opposite to the robot and saw themselves as teleoperators through the robot's perspective. This created a surreal sense of double agency as they simultaneously controlled the robot and observed their own body while doing so. Some participants described a dissociation of mind and body and a bilocated mind, disturbing certainties of self-location and self-identification between the robot and the controlling self. So overall, the implications of this study need to be explored further, while the data suggests a phenomenon which is known as e-autoscopy, an illusion in which the self appears to be bilocated in two places. These three illusion experiments revealed important insights into topics like self-localization, bodily ownership, and the plasticity of our sense of self, meaning that under specific circumstances, we are able to adapt to another body, even if it's an object, and perceive it as part of our own body scheme. These findings also have practical implications, such as influencing the design of more intuitive teleoperation systems that enable tactile feedback to a certain extent and allow a third-person perspective for self-regulation. The conditions are even helping to advance therapies for medical conditions such as phantom limb syndrome, for example, in the use of prosthetic limbs. So, what might these insights mean for the future of human-robot collaboration? In conclusion, by studying object manipulation, subjective sensations, and body illusion, we can gain deeper insights into the human adaptability to external objects. Practically, these findings can guide the development of more effective teleoperation systems for human-robot collaboration, improving the usability in fields such as healthcare, telepresence assistance, disaster response, or exploration in space. Theoretically, on a theoretical level, this research broadens our understanding of bodily aspects of social selfhood, presence, and perception. So at this point, I'm at the end of my presentation, and I'm happy to take any questions. Yes.
Thank you. Ilona, any question for her from the audience or the cloud? Dani?
Hi, Ilona. This is very interesting. One thing that I was wondering, so, I mean, the importance, what is your feeling on the importance of the haptic feedback? So trying to have systems which then also somehow might help the vision system in order to perceive better the sensation of the robot. So what is your somehow qualitative feeling? Is this necessary, or then at a certain point the vision system alterates everything? So what is your, because I mean, for a long time we have been trying to do that, but then we stopped. So.
That's why we did the rubber hand illusion stuff, or the whole body illusion stuff, because we wanted to see to which extent do people prefer to have a feedback, or what do they feel if it's in a certain moment synchronous. And they were like overwhelmed. They said, wow, this is so realistic. So I would say to a certain extent, also in the object manipulation studies, they constantly said, oh, so I'm feeling or I'm missing something because they didn't know how strong of which force they used when they touched the bottle or so. And it was constantly my job to stop them from hitting somewhere, or to modulate their force. Yes, and that's also why the mirror thing, or the third person perspective, could maybe replace this tactile sensation, because they had something where they could see their own position, they could see their own body and their postures and how they move. So they didn't hit their body anymore. I wasn't in panic when they touched something or they moved. It went smooth. So maybe a third person perspective could be a first step to avoid or to help somehow to deal with objects or to deal with moving in space. Yes. Yes.
We have another question from the audience.
Thank you. Yeah, the presentation was very interesting indeed. I'm wondering if there are some long-term effects, and you explore some dangerous effect, for example, when you feel the robot as your body, and you do some task that is dangerous, and then when you are in your real body, you don't feel the danger in some dangerous task, maybe. For example, touching fire, because you don't feel the pain with it.
Yes, maybe I should add this to my experimental sessions. How people are fearless when they control the robot in dangerous situations, and after that. So I think, no, I mean, this is like use it in disaster spaces or use it for hazardous environments. I don't think people will be fearless. But maybe they will be more daring to do it with the robot, what they otherwise would not do as normal human. That's my assumption, but I can do a little study.
Okay, let's thank again Ilona, and
Thank you.
let's proceed with the following presentation for the iFeel team. Enrico Valli.
Yes, I'm here on the cloud. I hope you can hear me, guys. So you should see the presentation, if you can confirm it.
We can hear and see you.
Okay, great. Good morning, everyone. So let's see what we have done in the last 3 months with iFeel. Okay, so first of all, just an overview of iFeel, especially for the newcomers. So the idea of iFeel is to create a set of wearables capable to retrieve information from the human body and give this data to AI algorithms that are capable then to estimate the stress analysis of the body, perform statistics, and also give input to avatars, in our case, iCub, ErgoCub, and then get back information from this loop in order to give feedback to the human. So mainly we work for this research increment in these 5 different topics. So the first one is the wireless suit. So we are adding a Bluetooth capability to the wireless suit. We are also creating a new version of the notes. And then we perform also some analysis related to some improvement that we can give to the sensor that we have inside. Then we work on the wired suit. We perform some mechanical design, improve some mechanical design for the interface between the mechanical and the electronics. We add Wi-Fi capabilities, and also we add the full integration with the BAF, which is the framework that we use for the biomechanical analysis. Then we work also on the iFeel shoes, in the new version of the shoes. So we are currently doing some manufacturing, so creating new shoes with different sizes. We also work on the standalone mode, so in the way that we can use the shoes without a receiver and also without the suit. And we perform a lot of testing in the force and torque sensors in order to evaluate the quality of the sensor itself. Then we work on the stressable insole. Actually, for this research increment, we made the paper, so the paper is ready and will be submitted soon. And then we have also a topic on test campaign. We are processing data from previous test campaign. We are, let's say, finalizing, hopefully, the documentation needed for the clinical studies. And then, we also plan to have new studies in the next month. All over, there is software design and product design acceptability in all these topics. moving forward. Okay, so wireless suit. So we had a couple of upgrades on the wireless suit. The first one is we create a node version 1.1 we call, because we extend the capability of the range, let's say, of communication using an external antenna. We are expecting to receive the sensors middle of February, so in the next few weeks we should have the sensor and make some tests. Then we are also working on adding Bluetooth capabilities, so we wrote some firmware on the current node, firmware on the receiver in order to receive data, Bluetooth, and then we do also some performance analysis. Then we also add some requirement, and actually we will start this research increment to work on the version 2.0 of the iFeel node. There are some changes with respect to the previous one. The main one we are adding a range extender, so in order to extend the range for the communication, the wireless communication. We want to add SD cards for some parameters configuration. We use a new microcontroller, and also we decided to move the battery recharging unit in an external board. Why this? Because we performed some tests, as you can see here in this video. We performed some tests, and we saw that the magnetometer got some drift in the case where the BNO 055, which is the IMU we used, is inside the enclosure, our case. We went a little bit more in detail, and we understood that the coil, which is the battery recharging unit inside next to the magnetometer, created drift. So here you see in the blue line a drift that is created by the coil. For this reason, we decided to move an external enclosure. Okay, related to the wire suit, as you can see here from this video, the wire suit is fully integrated with BAF. Currently, there is Bluetooth capabilities, but shoes are not Bluetooth yet, so we use a little trick here to make the full estimation, kinematic and dynamic, working on this with BAF. Next research increment, the idea is to integrate the shoes and the suit with Bluetooth. Then, in this video also here you see the way the mechanical design of the interface is done, and we made some improvement on this in order to make it more stable, changing some materials and make a little modification to the design. Okay, related to the shoes, I don't want to spoil too much because then there will be the vertical from Marco. So just very quickly, I would like to tell you that we are working we have been working in three different directions. The first one is to create this standalone mode. You will get more insight later on, but the idea is to avoid to use the receiver, so you can use the shoes wherever you want and collect data internally in the SD card. Then we perform a lot of tests with the output, with some, let's say, report of the test for each FT sensor. And then we create also a tool that is capable to analyze the FT sensors while this is embedded by an external company. You will get more insight later on in the vertical. Related to the stretchable insole, here you can see a video that is the video for the paper. So the paper is almost ready, I would say, probably ready, and has to be will be submitted during the next research increment. Okay, so finally we have test campaigns. We have three test campaigns running. The first one is with ISMA, the Italian Multiple Sclerosis Association. We perform a lot of data processing from the previous campaign, and we are defining now together with them the new protocol to be used based on the output of the previous campaign. Then still another never-ending story is the waiting for the payment of the Ministry of Health tax. So basically, we have to wait for this in order to be able to submit our documentation to the Ministry of Health in order to start this multi-center clinical trial with San Martino, the hospital in Genoa, and Villa Beretta. So the documentation is complete, everything is ready. We just miss these tags and the final grant from the ethical committee, which we should receive at the beginning of February. Then we also define a protocol with the Campus Biomedico for a new acquisition campaign in Rome. And the idea is to start this campaign in April 2025. Okay, related to the product design, as you see here, we worked on the modular charging station for the nodes. Here we have some magnets that are capable to keep together these modules, and you can add up to 10 of this module together in order to charge the nodes. This is quite handy, not only in the lab, but also when we have to bring our stuff outside the lab. Then we also work on the wireless battery chargers for the shoes. As you can see here, we modify a little bit what we have on the shoes itself in order to make easier, let's say, the charging of the battery. And then on the right side, you see here a new version of battery charging station for the shoes. Okay, related statistics. These are, let's say, the first statistic after the change to the GitHub project. So I don't think it's very easy to compare to the previous one. Also because we moved this during in the middle of the research increment. So I think we should wait for the next one to have more statistic, more clear and comparable with others. Moreover, as you can see here, also everything started somewhere in the middle of December. Moreover, we decided also to split because GitHub project asked for that. You had to split the human and the iFeel team with defined, let's say, repositories. So this is slightly different from the previous one. Okay, so I don't have many comments on this statistic at the moment. Okay, so that's it here. You can see the webpage of iFeel, LinkedIn, and email in case you need more information.
Let's thank Enrico. Any question for him? One from Daniele.
So Enrico, it seems that the battery and the recharger coil are causing together the drift of the magnometer, right?
More than the battery, I would say the coil, because we tested also with the battery, but it was not a big, let's say, drift. But the coil itself was a big drift. Yeah.
Okay, so this means that basically in Dario's suit, where is Dario? Yeah, so we shouldn't see. Exactly. We don't see these things. Okay, this is very, very promising then. Yeah.
Exactly, because I forgot also to mention, Danny, that we are working, we just start working on the new version of the suit, which is similar to the one that we use wireless, but is with the components that Dario is using on the wired. So let's say it's a tight suit, but then with the cable inside, and we just started now, and the idea is to have the final suit somewhere in the middle of the summer, I would say.
Okay. Thank you. So incredibly, I mean, the looser the suit, the better. Then, I mean, no, I mean that not the loser. I mean, the looser suit is better than the tighter, because
one is
not because of the looseness, but because of the other design. Yeah. Okay. Okay. Thank you. Let's thank Enrico again.
Let's welcome next speaker, Marco Forleo, and he's going to present for the vertical presentation iFeel team.
So, good morning, everyone. I will present the journey of iFeel shoes from robot for torque sensors to FT sensorized shoes. So from its original concept born in the research lab to the kickoff of its small production and beyond. After a quick introduction, we will dive into how iFeel shoes were created during the manufacturing phase, the challenges it overcome in testing, the last new features it brings, and what is in store for its future developments. First of all, what are iFeel shoes? To answer this question, we need to start with the origin of the idea. In the robotic labs of Italian Institute of Technology, a humanoid robot was equipped with innovative technology for measuring forces and torques applied to the robot to monitor and control its physical interaction with the environment. The revolutionary concept was to apply the FT sensors to the human body. Initially designed for robotics, this ingenious technology has been refined in both design and electronics to be adapted for human use and embedded in smart shoes to become wearable. This innovation has led to the development of a device capable of monitoring and analyzing the actions and forces involved in human motion, enabling the evaluation of key performance indicators in both industry and healthcare settings. In industrial workplace, iFeel shoes can play a significant role in preventing spinal issues and reducing the risk of injuries, especially in environments where workers are subjected to hard and repetitive lifting tasks. Also, in medical application, can be fundamental for the prevention, diagnosis, and treatment of various musculoskeletal disorders. The production of the iFeel shoes for series manufacturing was divided into two independent essential phases, the mechanical assembly and the electronic component integration. The mechanical assembly is where the shoe structure is created for robustness and durability. This stage required the end of our skilled craftsmen, thanks to them, to Gianluca for his valuable patience in using the glue to attach the Velcro on top of the nylon plate, and also to Alex, who did a great job handling the design of the new custom mechanics and also supported me in organizing the materials into packages and bags. Thank you, guys. We integrated the sensors and components into the shoe in the electronic assembly phase. This part of the process required high precision, and I had to rely on my unexpected soldering skills to ensure all connection. And I need to care about all the sizes of cable and materials introduced inside the housing of the electronics. And to use a torque wrench to tighten the screws with a specific force of 1 Newton meter, for example. So, a lot of detail. Thanks to this attention to these details, the electronic components fit without problems into the shoe, bringing the technology to life. As a result of this process, we successfully produced the 3 pairs of different sizes of iFeel shoes, which have already been used in demonstration to showcase their functionality and design. Additionally, created a detailed assembly guide documenting every step of the process. This comprehensive documentation can be used for future productions, ensuring consistency and high quality standards in every pair that we produce. So before the final assembly, all the electronic components were tested to ensure functionality and data quality. I tested a batch of 25 iFeel shoes 2 printed circuit boards, verifying the proper operation of the microcontroller, the correct programming of the flash memory, the functionality of all the MEMS on the PCB, such as the IMU module, the pressure sensors, the radio, the E2C bus, and also the read-write access to the SD card memory. I conducted tests for the String 3 electronic boards and for the system of these boards assembled on the FT sensors. And on top of the right, you can see an example of the results of tests conducted on a batch of assembled FT sensors. And the table 1 shows the functionality tests that identified, for example, the device with serial number 31 that we can see highlighted in red as having a failure in communication with the magnetometer sensor. So the other tables show the results of a statistical analysis performed on a sample to ensure data quality. And this analysis consists of calculating the sample mean and sample standard deviation of the data. And as we can see in the tables 2 and 3 reveal the anomalous high values in the electrical offset or data stability of some devices. I tested in total 50 iFeel Stain 3 electronic boards to check the functionality of all components and 20 to assemble the sensor to ensure data quality. So a lot of tests, so this important number has highlighted that we needed to develop a device to automatize this process. And so I developed a testing device for FT sensor system that automates functionality and data quality test with a simple touch. So it provides feedback through an RGB LED. So if we see a red blink for a functional test failure, a purple blink for violation of user-defined data stability limits, and a green blink for successful tests. Several parameters can be set via configuration files stored on the SD card, such as the identifiers of the sensor system, the number of sample MPG gain for the acquisition, and the threshold for the maximum offset value and offset variance of the data. So finally, the device generates a detailed report on the SD card memory, which is a text file that outlines the acquired data and test results. Now let's move on the new features introduced with version 2.0. There are three main features implemented in the last firmware release. And the first one is the automatic configuration of several operational parameters via JSON file stored on the SD card memory. And this feature enables the setting of offset values, calibration matrices, bias vectors, the type of communication protocol, the SB communication pipe channel, and so on. So it's also possible to store identifiers such as the ID for the electronic boards and sensor, and set the identification number of the shoe. So therefore, the user can easily edit this file to change the identity and the behavior of the iFeel shoe. Another feature I introduced is the ability to perform a tare adjustment for the electrical values acquired from the strain gauges. This is an offset zeroing calibration that involves pressing the user button while the shoe is resting flat without wearing it. This is important because it ensures that the electric offset values are recorded, accounting for the shoe's weight only, but without any additional load. And the last important feature is the addition of a third operating mode for the shoe. Beyond the demonstration mode, the demo mode and testing mode, I implemented a login mode, allowing the shoe to operate in a standalone without needing to communicate with any receiving iFeel station, but recording the data to analyze it, eventually analyze it offline. To start writing data, simply you have to press the user button on the iFeel shoe. And after pressing, the shoe synchronizes themselves via wireless SB communication. So the pressed shoe is the transmitter and the other the receiver, and both begin writing data to the SD card memory. The logic continues as long as the two shoes exchange the same acknowledgement byte or until the user button is pressed again. For every data written, a new increment of the ACK byte guarantee that the communication is synchronized, the synchronization is established between the two devices. So the next step will focus on implementing Bluetooth as new communication protocol for the integration with the iFeel wireless suite. The high-level software integration will be carried out to enhance the functionalities. And additionally, will be introduced for individual setting of each sensor to ensure accuracy and the reliability of the measurements. And that's all. Our look to iFeel shoes has come to an end, but their journey just began. So, as mentioned in the Air Jordan movie, a shoe is only just a shoe until someone steps into it. Thank you for your attention.
Let's thank Marco again, and if any question is from him, from the audience, I'm from Dani.
Thank you very much, Marco. Concerning the button, so what is the next
user
step?
button.
Yeah, user button. So are we going to integrate it? How far are we?
It's already integrated.
Yeah, but I mean, for the external shell, how do we want to integrate the external the button with the external shell then?
What do you mean for external shell?
Because then we have to design the external shell, right?
Oh, okay.
In the long run, how do you see the integration of the button with the external shell?
For the external shell, for now, we decide to stop it because the designing it's something that we can design. But
no. Yeah, but I just want to ask you, how did you see it in the future? I mean, how can we turn it on and off with the external shell? This was the question.
Can be done without problems if we have some suppliers that can customly design the rubber of the shoe.
Okay, so there will be a button there.
Yeah, can be.
Okay. Thank you.
Don't see it that way.
Other questions for Marco? Okay, so let's welcome on stage next speaker, which is Claudia Latella for the human team.
Good morning, everyone. I'm Claudia from the team Human, and in the next slide, I will present you the achievements and the activities that our team done in the past 3 months. So the Human team deals with the scientific objectives related to human biomechanics, from models, software and the development of software frameworks for whole body estimation algorithms. So let's start with the single team members activities. This was an activity of the torque computation for the human-human collaborative lifting. We acquired a data set in our lab with 2 subjects. The tasks were actually 3 lifting tasks. A lifting task in general, so without and with weights, incremental weights. The dataset has been acquired with BAF using the iFeel wearables. Before acquiring the dataset, we defined the NIOSH geometries from manual, and we decided, where the box lifted was placed in front of the human, the height of the weight, and the maximum height of the weight during the lifting. And we compute via the maximum posterior algorithm in BAF. We computed the lifting the joint torques at the L5S1, that is the lumbosacral joint, that is particularly vulnerable, let's say, during the lifting task. And our goal was to find a correlation between the estimation of the torques of this particular joint torque with respect to the lifting index. And actually, we gathered this result, that the joint torques at the L5S1 increased proportionally with the lifting index. So this activity has been completed, and the objective now is to put these results in the submission of the iFeel technology paper. The second step of this analysis dealt with the definition of a KPI for the NIOSH lifting index. We wanted somehow to define, to infer the task geometries from the kinematics of the human and not for a predefined Excel table, let's say, no? So we gathered the kinematics of the human, of the subjects actually from the data set. And we wanted to see that there was a correlation, a similar correlation with the lifting index. But the lifting index estimated via the KPI did not reflect the actual lifting index. And this was because actually we found that our kinematics was not so good. I mean, during the lifting task, there is a moment in which the subject grasps the box before lifting, and the position of the hands at that moment should be more or less the height of the box, and this was not. And we performed an analysis on the kinematics of the hands, actually not both the hands, but also of a middle point between the hands, and we found that the height of the box was different. So this was actually the trigger for another activity that Gianluca and Ludovica started on the model optimization, because we thought that if the kinematics is not working, if the results are not good, let's say in this way, probably could be a problem related to the model, also to the sensors, or a combination of the two. But we started investigating the model for the time being. So we acquired a new data set with a subject in the lab. We performed simple tasks, an N pose, T pose, and pose. This was the first task. The second was torso bending with no DOF motion. I mean, try to mimic a lifting task without using the joint of the torso. So something very, fixed, with the torso fixed. And the other task was with using all the joints all the DOFs in the torso. Actually, what Gianluca and Ludovica did was to use a different model, just to understand if the model was the previous problems, no? Because the model, the left-hand side model you see is the model that we obtained via the human model generator tool. And this model is a model that is built by providing a subset of measurements of the human, mainly the height of the human, and the model is created via the anthropometry, no? And clearly it does not fit perfectly the human subject. So the alternative was to measure each single link of the human and to create a measured model. So, and we ran the analysis using both of them, trying to understand if this could be the error. So in the first task, for example, we saw that the realistic model was the one measured as expected, and the error of the human model generated model, the anthropometric model, was about 3 centimeters. In the task without using the joints, the DOFs actually of the torso, again, the realistic model was the measured model, and with respect to the other one, the error was more or less again on 3 centimeters. And we say that the model is more realistic because during the bending, we know the height of the box that the hands were touching. So, and it was more or less 49 centimeters. So again, this was a proof for us, a tangible proof for us. In the third task, there's something strange because both models are wrong. So in this case, the difference is that we used all the joints of the torso. So probably, there are two ways to be investigated. One is the way in which we modeled the torso, because we now modeled the torso in 3 pieces, in 3 blocks, the pelvis, the lower trunk, and the upper trunk, so only 2 joints. And probably we can add more joints, or the position of the sensor on the pelvis. The pelvis is the base of our model, and the physical position, location of the sensor attached to the pelvis sometimes could be attached, sometimes probably is attached to the lower trunk, yes, the lower trunk. So probably we need to understand and we need to do more analysis on this. This is the part of Cheng. I mean, Giuseppe already did the activity of Cheng, but I mean, here I put the data set he acquired with one subject in the lab. Is in a walking test. Was a walking test. The data set was has been acquired with the Xsense iMuse, the full set of iMuse, but only 5 have been used for the prediction algorithm. And this is the video of the result. I mean, in the red avatar is the prediction. The blue avatar is the ground truth, let's say, and the red avatar is the prediction. And you see the plot of the joint position and velocity of the left knee. And now, I mean, we can say that this part of this prediction for 1 second is working. The next step is to integrate the extended gamma filter framework for tracking and prediction the pose and the velocity of the human base. This is the activity of Antonella. Antonella is trying to model the tendon in the muscle. Why this? Because she started to do the muscle optimization, and at a certain point we found that the optimization was not good, and one of the possible cause of this is clearly that there are 2 inputs. The sensors, in this case, the sensors are iMuse for us and EMG, or the way in which we model the muscle. We model the muscle only considering the muscle and not the tendon. Actually, and we are using the term muscle in a not appropriate way, because we should use from now on the muscle tendon complex, because the muscle is not only composed by the muscle fibers, but only from the tendons. So the tendon modeling implied a change, a modification in the muscle contraction dynamics block of this pipeline. And the first step was to include inside the code, inside the implementation of, oops. I can see the presentation right here. I try to reconnect because I see the presentation on my laptop. Okay, it should be okay right now. So the first step, as was saying, was to implement the part of the tendon that is missing in the heel time model before. The second step is to verify that the force of the tendon is equal to the force of the part muscle, okay? And to doing this, literature provides the several algorithms. In this case, Antonella is evaluating the Newton-Raphson algorithm, and this means so to add the block of added in the right-hand side of this slide of the Newton-Raphson algorithm, because in this case, to compute the length of the muscle tendon complex, the force feedback of the muscle is needed to verify the step 2. So this is the work in progress. I mean, the activity that Antonella is doing, also comparing and benchmarking the length of the tendon using OpenSim. Okay, now there is the part of the statistics. So I decided to plot these two cumulative flows. One is for the closed issues, and more or less there are 10 issues closed per team member during the past 3 months, and the opens one are more or less constant. I mean, is not there was not any strange behavior. Related to the burn down, sorry, I decided to plot on the left-hand side part of the slide the closed issues per sprint. As you see here, is missing sprint 2 because I opened the sprint 2 in the project, but I forgot to assign to the issues to pass the sprint 1 issues to the sprint 2. So actually the sprint exists, but nothing has been assigned to it. So this is the explanation of also the big amount in the sprint 1, because that sprint should be actually split into 2. And the closed issues per labels identifies, this plot identifies more or less that there is there was a number quite high of issues closed for the implementation, probably related to the part that Ludovica will explain in the vertical presentation, because there was this porting of the KPIs in the Python code. So there were a lot of issues opened and closed as implemented issue, as a phase implementation. There is a huge amount in experiments, because as you saw, we performed a lot of dataset acquisition, and also for phase management. I think that the reason for the phase management huge number is because in the team human, we decided, as Enrico previously highlighted, we decided to put all the PNRR project, total spine, NR twin. So in this phase, in the phase management, there is a lot of work of managing this project, actually. That's why. And this concludes the presentation of the team. If you have any questions, I'm here. Thanks.
Thank you, Claudia. Any question for her from the audience or the cloud? Okay, in this case, let's go on with the next speaker, which is Ludovica Danovaro. Vertical presentation for the human team. Let's welcome her on the stage.
You see it? Okay. Good morning, everyone. I'm Ludovica, and today I'm presenting my work on evaluating the healthcare and industry's KPIs using wearable sensor for human monitoring. Let's introduce the topic first. In this presentation, we will explore how the use of wearable sensor can contribute to the evaluation and monitoring of KPIs that are the key performance indicators in 2 main areas, the healthcare and the industry. The KPIs are metrics that are used to evaluate specific aspects of performance or behavior. And depending on the condition that we are analyzing, we can consider a different type of KPIs. Often, they are based on parameters that are established in scientific literature. In the healthcare context, we are collaborating with the ISM Association in order to consider and analyze gait parameters in patients that are affected by multiple sclerosis. In fact, the goal is to better understand their difficulties in the movement during the walking cycle. In parallel, in the industrial context, we are using wearable sensor in order to assess the risk of physical strain injuries in the workplace. And these KPI are very important in order to improve the safety and prevent injuries. My work was based on porting the code for the implementation of the walking KPIs parameters from MATLAB to Python. Moreover, I implemented the NIOSH lifting KPIs parameters in Python. And here there is the link where you can access the code. Let's now pass to the walking KPI parameters analysis in detail. The first one is the cadence, that is the number of steps that a person can perform in 1 minute. The second one is the cycle duration, that is the time that passes between one foot strike and the subsequent one of course, the same foot. Then there is the stride length, that is considered as the distance between successive points of initial contact of the same foot. The next one is the max angular velocities, that represents the maximal angular velocities of the leg, of course, of the left or of the right during the swing phase. We can pass to the swing width, that is defined as the ratio between the lateral displacement of the foot during the swing and the stride length. The next one is the path length, that is defined as the 3D distance traveled by the foot during the swing compared to the stride length. The last ones are the stance phase and the swing phases, and they are respectively the entire time that the foot is in contact with the ground and the time where the foot is in the air. Let's now pass to the NIOSH lifting KPI parameters. The NIOSH lifting equation defines the recommended weight limit. This parameter is a recommendation of the heaviest load that a healthy worker can lift without increasing the risk of developing low back pain. In this equation, there are many factors. The first one is the load constant, that is the maximum recommended load weight that can be lifted under ideal condition. Then there are the horizontal, the vertical, and the distance factors that depends on the geometry of the lifting task. The frequency factor depends on the time between the lift or the frequency of the lifting. Then there is the asymmetric factor that depends on the angle of the load between the load and the body position. And the last one is the coupling factor that defines the quality of the grasp. That could be good, fair, or poor, and it depends on the body position. Directly from the recommended weight limit, it can be derived the lifting index by using the weight of the load that could be lifted. The lifting index in particular identifies how dangerous the lifting task that is performed is in terms of potential of risk of injuries. Let's now analyze the result. Let's now analyze the result obtained for the walking KPIs for the patient 05 during the trial 21, in which the patient performed a 7-meter walking task. Specifically, we are focusing on the swing and the stance phases that are two very important parameters during the gait cycle. Patient 05 is affected by multiple sclerosis with EDSS 04. The EDSS is the Expanded Disability Status Scale, and he has a score of 4 that represents a high level of disability. In fact, this score results in a gait pattern that is quite different from what we could expect from a healthy person. In fact, typically the stance and swing phase are distributed symmetrically between the two legs, and the percentage are usually of 60% for the stance and 40% for the swing phase. However, in this case, we observe an asymmetry between the two legs, both in the stance and in the left and in the right leg, and we can show that the values are quite different from what we expect. Now let's analyze the inter-subject comparison across all the trials. This figure provides an overview of the stance and swing phases for different patients, highlighting a variability in gait patterns. By comparing this KPI across the subjects and all the trials, we can understand how the level of disability that is shown by the ADSS, can affect the gait asymmetry and also the motor performance. Let's now have a look at the result of the Nios parameter for the lifting task. As we can see in the figure on the right below, we can see that the lifting index remains below the value of 1 for the entire period of the lifting task, which aligns with our expectation that are based on the geometry of the lifting task and also of the weight on the weight that is lifted during the task. This result indicates that this specific task falls within the safe lifting range for a healthy worker. Let's now pass to the conclusions. We can say that now all the KPIs that were previously implemented in MATLAB are available in Python, and moreover, also the Nios KPI have been added. In particular, the KPI calculation has been converted into a Python library, which will be integrated into BAF. Here we can see that there is the pyproject.toml file that has been crucial to convert the KPI calculation into the Python library. This file defines the configuration for building, packaging, and installing the library. For example, the project section specifies the name, the version, and the description of the library together with its dependencies. As last, the project scripts section creates a command line interface linking the BAF KPI analyzer script together with the main function of the BAF KPI main module. This modification allows the user to run the KPI analysis directly from a command line. And this change makes the code much more flexible and usable, because a key aspect of this transformation is that the code is more generic and no longer limited to a single use case or a specific data set. In fact, it can be easily adapted to every needs, and anyone can integrate the KPI calculation into their own workflow. Thank you for your attention.
Ludovica, question for her from the audience?
Ludo, so these KPIs can be also used by the walking guys, right? So if we want, no, also Fabio, why do you point on Giulio only? Only you, also you. So if we wanted to evaluate better the performances of somehow the ankles, the walking, etc. So theoretically, we might use this.
The library, the Python library, yeah.
From BAF.
From now, as so far, is in the element iFeel repo, but will be ported in the iFeel the BAF library.
Cool.
I will talk to Silvio to do that.
Okay, thank you.
Thank you.
Thank you. Ludovica again.
Let's thank Ludovica. We are 5 minutes in advance. So for people from the clouds connecting right now for Carlotta, maybe they will be disappointed. So anyway, next speaker is Carlotta. Which,
I start with a setup that could take a lot of time.
Yeah. She will do 2 presentations in a row for the DARWIN team, both the horizontal and the vertical.
Marathon.
Ah, yeah, okay. Okay, so tonight for the dinner after the research increment, what we have to discuss? Claudia already booked it, no? Ah, just the time, okay. So they can call, if people from the cloud want to join, they can call Montalegro and ask for additional seats. Yeah, the reservation is name of Claudia Latella for 9:30 this evening. We are assessing the opportunity of doing aperitivo.
I'm waiting for another computer because I have issues with my computers. So we can still discuss about aperitivo. I know a few places close by. Where are you going? The Grappa. You can go to Calice, Castellette. No, c'è qua il caricatore da me, cavolo. Cioè, prendi anche il caricatore.
L'aggiornamento.
Not I can.
Su Teams.
Stai vedendoti? No, fai prima le milestone, ce le hai sempre lì. Almost there. Se proprio se lo fai open? Artificial Mechanical Intelligence. DARWIN? Che mai sta? Aspetta. Sta ancora. Scera che mi prendo. Okay, wasn't easy. Can anyone in the cloud confirm that you can see the screen or someone here double check? Silenzio assenso. Ok, silenzio assenso. Hello everybody, my name is Carlotta Sartore and I'm here to present the DARWIN team objective. A DARWIN is an acronym and it stands for Differentiable Architectures for Robots Whole Body Intelligence. So which is our mission? Let me say this is a little bit a really high level mission that is the moon. What we would like to do is leverage differentiable architecture and hardware accelerated simulators to determine hardware and motion requirements for next generation of humanoid robots, incorporating human data as guiding constraints. Okay, this is a really long sentence. What does it mean? What we would like to do in the DARWIN team is use the internal developed simulators that exploit the hardware acceleration, so GPU and fully differentiable thanks to JAX, in order to do co-design, so identify optimal hardware, motion, and behavior for humanoid robots. So we are quite close to the ankle team. We are aiming to be close to the ankle team, so this kind of team that then help in the mechanical design for the robots. And since our idea is also, we saw before Claudia teams and Ludovica presentation, we saw the human doing stuff that currently our humanoid robots are not able to do. So the idea is also to warm start our co-design framework with the modeling and all the work that Claudia and the human team generally is doing. As I was saying before, this is the moon. We are far away from that, but this is where we are aiming to. So which is the team? The team. I apologize with Omar. I saw that around other kind of pictures, but I took it from GitHub. So this is the main developer team. We have also Stefano, Giuseppe, and Silvio that is helping us in the support team. But the main developing team consists of myself, then Filippo Luca Ferretti, which is dealing with reinforcement learning for co-design in particular. Then we have Omar that freshly joined this research increment, dealing with SimTutorial. Then we have Alessandro Croci that is dealing with simulation infrastructure, so the main developing from JAXsim. And then we have Lorenzo Conti, which is dealing with the more classical co-design method, exploiting derivation of fully mathematical of zero-order methods. So what has happened since we last met? We start with Alessandro, and we had one milestone that was but was really huge, let me say, that was support closed chain dynamics in JAXsim. This was aiming, as I was saying before, to start being able to be of support for groups developing the mechanical part of the robot. So the Ankle team is dealing with the closed chain dynamics, and the first step was, okay, let's support. It is not easy, let me say. As you see, we can say halfway there, and what happened in this research increment is that Alessandro studied and explored a lot. Closed chain dynamics is supported currently in Pinocchio and Gazebo, which are two simulators which are neither hardware accelerated or differentiable, so they're different from ours, but they have a math to support that. So he did a lot of studies, so if anyone is interested in the mathematical modeling of the closed chain dynamics, you can go to talk to Alessandro. And now he's starting introducing it into our framework and our simulator. Then we have Filippo. As I was saying before, Filippo is mainly focused on reinforcement learning. We closed one important milestone that was to have complete the architecture for performing reinforcement learning with JAXsim in the so-called GYM library, which is spelled with the JYM, I would say, okay? And that's done. Then we have three different milestones that are aiming to actually make the robot from a high level, make the robot walk in JAXsim with the RL and start putting co-design into it. So we have a replicate, a milestone aiming at replicate ErgoCub walk in RL plus IMP on JAXsim. So we saw before a lot of videos of Giuseppe and Giulio's work with the Isaac Sim, and we want to replicate the same kind of infrastructure in JAXsim as a starting point. Then we want to start to add hardware parameters to the RL loop on JAXsim. JAXsim already implemented parameterization with respect to the hardware parameters, but putting in the reinforcement learning algorithm is not easy, since theoretically each robot should learn its own policy. But we are working on that. There are a few ideas that we are currently tackling. We need to further investigating them. And then we investigate utilization of gradient-based method for hardware optimization in JAXsim, because as I was saying before, JAXsim is fully differentiable. We have talked about co-design is not the first team that talks about co-design, but usually zero-order methods are employed to the nature of co-design issues, the fact that you have discrete variables, you have difficulties in deriving the gradient mathematically speaking, and our idea is to utilize JAXsim that per se gives this possibility in an hardware accelerated framework to employ gradient-based methods for co-design. So from high level perspective, what happened during this research increment is that before the robot was imploding, now through RL, we are making, okay, let me be fully positive, we are making one step. I know you will say it's not one step, but for DARWIN team it is. So please don't ruin our dream. This is the first step towards something that is starting working, and we are quite eager to see where this will go and to put the other parameters in it. Then we have Lorenzo. Lorenzo is dealing with more, as I was saying before, zero-order method, the more classical co-design methods. For studying the leg, we saw before in Giuseppe's presentation, he's studying the passive walker, which is a body part that is able to walk only exploiting the hardware without any motion control architectures. So it's the embodiment, let's say, of what we call hardware intelligence, so where the intelligence behavior arises only from the hardware. And this is what Lorenzo is trying to do. He's trying to understand how to port that kind of ideas to humanoid robots as we have in lab. We closed one milestone, which was implement architecture for zero-order optimization of passive walker parameters using Komodo, so the infrastructure is there. We have a second milestone that was optimize passive walker hardware parameters, so actually use this optimization, which has been put a little bit on hold because we focus on investigating the mathematical equations governing, there is not an F, there is a G, the passive walkers dynamics, and this is what Lorenzo is focused on, so deriving the actual math, and also writing the thesis. So we saw before, we also with Giuseppe, we have a compass walking. This seems a simple compass walking, but actually this derives from the mathematical equations on how a passive walker can walk by itself. And instead on the right, my right part, we have the passive walker. So what actually translates into a mechanical design. Then we have Omar. We already closed its first milestone, so welcome to the team. I think that for Omar it's been quite a full 2-3 weeks, and he got fully acquainted with JAXsim, I can say, and with the JAXsim infrastructure. So this is an opportunity for welcoming you again in the team and in the whole HAMI team. And then we have what vertical presentation is about, and what I think all of you saw us a little bit wondering about with crazy faces in the week before this one, and is the JAXsim sprint. We have a vertical presentation on this, and we did the sprint to improve JAXsim modularity, speed, and readability. So statistics. DARWIN team is a new team, so these are the first statistics we are seeing. These are the history points, and we can say that we have been quite constant, but for this third sprint, which was coinciding with the Christmas holidays. And for what instead concerns the cumulative workflow, we have been, I think we quite aligned with a few plateau with the linear constant behavior. We have some plateau. For the Christmas holidays for sure, and also through November. I don't know actually what happens in that week, but whatever it happens, it happens. And humanoids. So we were in France. Okay. And then we have the best cumulative workflow we had. Is interesting because it was just when we came back from holidays, so it means that the holidays were a good things to do for us, let me say. And the worst one was instead the one for Christmas, which has completely sense. Let me say that what I think we did a good job in this increment. What I think is our main issues is that we are all optimistic and enthusiastic people that thinks to do a lot of things in a research increment. So we should also try, and I put myself also into it, more into it, to define achievable goals. I think we are struggling a little bit in this, but there is space for improvements. And so now we have a vertical presentation about how we improve JAXsim modularity, speed, and readability, and we were finally able to simulate a bunch of robots in parallel. And this ends the organization DARWIN general presentation.
Thanks, Carlotta. Questions for now, for her? We are even more in advance now.
The sim to real, how do we intend to face it in the next 3 months?
Okay, the sim to real, the idea is to, what we are foreseeing is DARWIN team also to start going to the real robot for sure. People in the DARWIN team should have the sensibility of real robots. And what we were thinking is tuning the simulator parameters. There is a bunch of parameters hidden in the integrator, in the contact models, in order to fit real data, so that we collect on the real robot walking or whatever.
Yeah, it would be nice that Delta and Darwin DD do a sort of fusione. Have you ever watched Dragon Ball? Yeah, for a certain point, because I mean, it would be nice that these tools then are also used to generate reinforcement learning. But this is something we can plan in the future. Okay.
Sure.
Not becoming the same thing, but just like a joint objective. Good. Collaborations. Yes.
Other questions? Okay, next speaker is Carlotta. You have 5 extra minutes before the lunch break.
That I have to wait.
Yeah,
yes.
let's wait a bit.
Aperitivo.
So I remember everyone tonight's dinner, 9:30, Montallegro restaurant.
How to reach Montallegro. There is the vertical transportation starting from Zecca. And for people that are resident in Genoa, it's free. But you have to remember that starting from January, you have to ask for the abbonamento. It's free, but you have to ask for it. Faccio pubblicità di Genova, abbiamo la lanterna. Non l'avevo vista.
We're waiting 1 more minute to be more close to the schedule. To be closer.
There is a doc. I don't know who left it here since we have one of them and another one. Speakers. È tuo? 5 punti cop. Colgo l'occasione. Io avevo 2 punti cop. Posso iniziare? Okay, I think we can start. Le mutate te. Okay. Okay, I think we can start. So, hi everybody, I'm still here, Carlotta, and I'm still here to present the vertical presentation for the DARWIN team. Let me say that I'm here presenting the work of the whole team, so only as a representative and for, but what we will see in this presentation is of the whole DARWIN one. So our presentation is entitled When Hardware Acceleration Isn't Enough, Improving JAXsim Usability, Modularity and Speed for Co-Design and Reinforcement Learning, or How We Learn to Stop Worrying and Love JAX. This is actually our story. We start the sprint, and then we will see quite sad and frustrated, and in the end, let me say, I start seeing some happy faces on myself also. So first of all, what is JAXsim? JAXsim is a differentiable simulator fully written in JAX that supports CPUs and also hardware acceleration, so working on GPUs and TPUs computations. As I was saying before, there are 2 main characteristics in JAXsim. One is the velocity, so it allows to be parallelizable, exploiting GPU, as it is, for instance, JAXsim, but also it is differentiable. And when we call differentiable, is not only differentiable with respect to the robot state, so what we usually express with Q, nu, dot, but also with respect to hardware parameters, what we would like to express with respect to pi, let me say. So why JAXsim? This is actually overlaps with the scope of the whole team, so this is the reason why we are fully in love with this simulator. Is that what we would like to do is combining optimal control policy learning, reinforcement learning with optimal hardware parameters, so optimization of hardware parameters, exploiting such simulator. So what does it mean? It means to warm start everything with the human model, as this is this, thanks for the videos to the human team. I saw it from your issues. And for performing something similar to what the Delta team is doing, thanks also for this video, and explore in performing co-design. This video actually is a video of the genetic algorithms that we did in the past, but the idea is to replicate this also exploiting hardware gradient-based methods for the co-design part. So what were the issues? Everything I said before, it's really cool, and it would be super cool to obtain it, but JAXsim was quite slow. These numbers are not super precise, but it was taking us 1 second to simulate 0.001 seconds of a batch of 564 robots. For those of you who have worked with learning knows that the basic of learning is having a lot of synthetic data, and you need to generate them fast. And this was not the case. So the results was frustrate people, let me say, and also that the robot behavior we were able to achieve was as the one in the picture after weeks of training that actually translates into few minutes of life for the agents. In addition, another problem was that the code was complex. There was only the main developers knew the secrets, knew how to deal with it, and every time a new people went there, I don't know the sentence on that. These are ChatGPT generated, and let me be sincere. And every time a new developer was joining, was trying to figure it out, it was super difficult, and sometimes also difficult to forget what you just learned. This also made it difficult to add new utilities, because every time someone wanted to, also someone external to the DARWIN team wanted to add something, it was quite discouraging for him, her to get acquainted with the tool. So what we decided was to do it a sprint. A sprint is 1 week. We did a 1 week sprint because characterized by stand-up meeting and the fact that we were all together in one room. We were sequestrati, kidnapped, we can also say. And we have a main development team, which was myself, Filippo, and Omar that joined for 1 week and then was sequestrato. I'm sorry, Omar, for that. And then we have Alessandro. And then we have a support team of Lorenzo, Silvio, Giuseppe, and Stefano. So our goal was to improve JAXsim usability for non-expert users, and also to improve JAXsim execution speed. So trying to take 2 birds with 1 stone and having something manageable for us and for the main developers, but also creating something that can be useful also apart from the main development team. So this was our plan at the beginning, and let me say I'm quite happy that we actually, let's say, we stay strict to it. We had the first part for understanding the code, a second part that we call the deconstruct phase, in which we start removing things with no mercy, let me say at the beginning, in order to have something manageable that we were able to debug easily and that contains the minimum amount of rows needed for our work. And then we start back the construct phase, adding the things that we thought were useful and in an understandable manner. So what does it mean with the construct phase? We start by sacrificing code elegance to prioritize usability and readability. JAXsim code originally was using a lot of elegant code that was difficult, but could be difficult for a non-super expert Python programmer to be understandable. So we start by removing things and make things as simple as possible using the basic Python structure, but readable. This translates into actually shrink a lot of things. So we pass from a big nested code to a quite skinny code, let's say. Then we sacrifice code generality to cut down on computations. JAXsim originally was aimed to work both as a simulator, as a dynamic library, and as utilities for robot control. we decided to concentrate on simulation. So what does it mean? It means that for being all that stuff together, every method needs to be general. So it needs to be self-contained and workable by itself alone. This is something that it's good because you can take things and use in another part without knowing so much about everything and with all the generality you want. On the other hand, this meant for what the JAXsim was that you needed to do a lot of computation several times. So what was happening is that we have data, and that data was updated. That the update method computing all the kinematic of the robot, to talk about practical example, every time you needed to access something on data. And when you want to simulate a dynamic, when you want to simulate contacts, this means calling those methods a lot of time. So we decided to lose generality because right now it's not so straightforward to take this as a cost, let me say. You cannot take every method and use it wherever you want, but we have a single update method for data and we cached the variable that we need. And this actually was quite useful, as we will see before, in decreasing the compilation and the runtime. So we had a lot of PR, and this was to giving the idea of what we mean with the construct phase. We remove something like 5,500 lines. As I was saying, we were a little bit without any mercy at a certain point. And this was also something that maybe could be improved in the past, being less deconstruct. But we did a lot of PRs. We had a branch for our sprint, the sprint dev, and we try to do continuous merge in that branch every day, maximum every 2 days, so that we were fully aligned with code. And it didn't happen something like I have a branch, Filippo has a branch, Al has another branch, I'm another, and then we found ourselves at 6 p.m. on Friday. How can we merge this? It's impossible. So the idea was continuous merging and continuous testing. This is something that we overestimated it before starting with sprint, and let's say it was really a lifesaver. It was something that we did a retrospective, and all the members in the team raised as a good point that we were lucky. Let me say we didn't implement anything. It was work in the past. We had a lot of tests to be run. And my suggestion also, and the suggestion of the whole team is that we not only have continuous integration tests that test the functionality of a single APIs, but we always came back to the most complex case, which was the robot walking. Because what happens a lot of times is that all the tests were passed, but when we went back to the robot walking, it didn't work anymore. So we need to come back. So always take, when you do these kind of things that are quite aggressive, always test on the most complex case, because there are things that you cannot test with simple cases. But for debug, the simple cases are the saver, because if the simple cases are not passing, there's no way that the most complex one are. So this was the output after the deconstruct phase. JAXsim is JIT compiled, so we have a compilation part, even though it's Python. And we were able to pass from 42 seconds, let's round it, of compilation time to 11 seconds. And this could seem something not super useful when you're talking about learning, but it becomes useful when you talk about co-design, for instance, because a new robot right now means a new compilation. So having this manageable, it's of key importance. What instead concerns runtime, for 6 seconds of simulation, we pass from 60 seconds to 30. There is parentheses with 12 because we were able also to be more robust to increase the time step to 1 milliseconds. And this means that we halved furtherly the execution time. All of this was on CPU. And let me say that if you're working on GPU, you don't want to go on CPU because things that are fast in GPU are super slow on CPU. This is also Mujoko. There is Mujoko and MJX for a reason, because one is for CPUs, the other one for GPU. So we are working on GPUs, so we start the construct phase. We say, okay, now it's the time, we have something readable, we have something that we start to understand. Let's construct and let's go back to the our main goal, which is also GPU. And our first step was to implement a new step method characterized by modularity and readability. We made the first step, the step composed by 4 different blocks. One is the computer resultant torque, which in the future we also think about including motor there, so that it's could be quite easier. Then we have a compute contact force that right now implements the relaxed rigid model, which is a rigid model that adds a regularization term depending on the object proximity. And but the code, like here, we are aiming in the next days to implement the rigid and the soft contact. It should be easy, something like plug and play. Then we have the compute system acceleration, and then we have integration, and we move towards a semi-implicit Newton-Euler, which is the easiest one you can implement, but for our use case, right now it's working. Then, as I was saying before, our idea is to have something modular. So if something is not enough and you have the need of something else, you can simply, with a lot of quotes, remove one part and add another method. So everything should be quite modular. One good thing is that the refactory implies only adding 200 lines of code, so we were still able to keep the skinniness, I don't know how to say it, but the code was quite, only the important part were there, that it's good also for the, this is something we are currently developing, so we wanted something that still is manageable also right now. Then we move towards the test on GPU, and let me say that we learn in the hard way that GPU doesn't love at all CPU, and this is also ChatGPT, thanks. And ho rotto il microfono. Scusate. And what we learn is that you have to be super attention to transfer from GPUs to CPUs. We found out that the logging system we were using, the exception system was passing through CPUs. This also in main. And that was what was really slowing down stuff. What was taking 1 second for simulating 1 millisecond. And we also found out that we were in the small details where we were casting twin stuff. So it's super messy. So my suggestion also here, what we learned is that every time you work with GPU, check the transfer to host, so to see where it goes, and never underestimate what a cast can do and what an exception can do. Then when we optimized this, we were finally able to simulate a bunch of robots, and I don't know, okay, ce l'ho fatta. And these are the actual results. Okay, the video are starting. Okay, grazie. And if we have a video where we compare JAXsim versus MJX, this is on GPU, and we have the steps per seconds, and we have the batch size. We are talking about humanoids batch size. And we have in blue JAXsim sprint, so after the work we've done. In green JAXsim main, after, which was the start point, without the passing through CPUs that we remove it for fair comparison. And we have MJX. And we can see that, first of all, now JAXsim and MJX are comparable for small batch sizes. So we can start actually using that for learning without the problem of before. And also that we scale better, most likely because MJX, we scale better with respect to the robot simulated, most likely because the MJX saturate the memory. And this could be the reason why we instead are linear with respect to the batch size. All of these results are on the server we have, so for giving you the idea that we exploit quite fast GPU, but all of them were with the same kind of hardware. So they should be quite comparable. So last part, the lesson learned. Thanks to teamwork, you can obtain results greater than the sum of the results achievable by each single individual. This is a site of Xera 95 for you may aka Alessandro, and I like it because I like also that the idea was that we did something more bigger, because it seems like we're saving a life. We're not saving a life, but we did a developing work bigger with respect to if each of us alone work in on our desk, and then we start merging things. Another one is have a clean commit history, because Git remembers, but you may not. And we were the one that did not remember, sincerely, because we use Git remembers, but in the end we were having a Git history with a lot of commits, work in progress 1 for content, work in progress 2, and in the end, when we wanted to bisect and we found some issues, it was really a mess. So my suggestion is Git remembers, but try to also to help with the clean commit history. Then the continuous integration test is the solution to fast development. This is something you always study when you do computer science, but now we learn it on our skin, and let me say that it's absolutely true. All of this work couldn't be possible without a continuous integration, continuous test. And when things get complicated, better to remove things rather than add. Sometimes it happens, I think, to all of us, that you are really into something and you think, if I add this line, if I add this debug, maybe I can fix. When you find yourself really forced not to find a solution, start removing stuff rather than add. And I think this is the way, at least it was for us. So what's next? Now we can actually start doing co-design, warm starting with human and learning. So I think I talk for the whole team, we are quite eager to start doing that stuff and use JAXsim rather than clean up JAXsim. But the sprint was a really good experience. I talk for myself, but I saw the happy faces after during the sprint, and I think it was for all of us. So thank you, and next time let's make a picture so that I have a nicer last slide.
Thank you, Carlotta. Questions for her from the audience? From Silvio.
So thanks for the presentation. Actually, I have a question that I always wanted to ask you during the meetings, but I forgot, so I ask you now. In the comparison with the MJX, which kind of collision mesh was MJX using? The same 4 collidable point of JAXsim or what? Because if it was using all the meshes that could have, let's say, contributed to the saturation of memory.
It's a nice question, and I should double check. I don't know, because you know. But we have someone that knows. Bravo. Filippo said MJX is limited to 200 collision point.
As far as I remember from the documentation.
So that
we are using
no, more than 8.
18, I guess.
More than 8, for sure, more than 8.
Or 16, I guess.
16.
Or like 8 per boxes per.
We should double check.
So, yeah.
I think that what he was saying completely makes sense. No, I agree. Also, when you say saturate, you mean saturate per robot or per batch robot? 200 the collision point saturated.
I think it limits like taking the. I'm not sure actually.
Okay, we should double check. Thanks, Silvia.
Documentation.
Other questions from Marco?
Thank you, Carlotta. Just a curiosity, how many tests for the continuous test integration you do, and how much time it requires?
Okay, basically, I think it strictly depends on how you organize the work. We were organizing, it was a teamwork divided by 2 and 2, so couple, and each couple was dealing with its own flow of development altogether. But let's say, for instance, I was mainly working with Ale, and me and Ale, every modification that we think was impacting, so semantic, so moving stuff around, we were double checking with the robot working. And if the robot was not working, we're coming back to continuous integration. For sure, we were trying to do it every end of the morning and before merging in the afternoon. So we had the point in which we were doing a recap of what we were doing. We were stopping a second to see where things were going, and we were looking at the integration for the last commit. So this, you need to be a little bit systematic, in my opinion, even though we were a small team. But at least before merging in sprint dev, that's the minimum, what we call sprint dev. So the main branch for the development was the minimum requirements that we pose ourselves.
Okay. And what's the number of the tests?
203. Okay. But let me say that we were running them, then we were thinking something was failing, we were then running single instances, so it's not that every time you need to put 200. And with the work done, we were also faster in performing the tests. This was also something that we saw.
Okay, thank you very much.
Can I comment on this just because I sometimes fear people that say, we're not doing tests, we should do a lot of tests, and then you're blocked. Because doing a lot of tests takes a lot of time. I need to do the work, I have the deadlines, I never have time, blah, 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 blah. Oh no, blah, blah, blah. And then people just complain. Then that's, I know that we're in Genoa, but in my opinion, complaining and not doing anything is always the worst possible scenario. Complaining and doing something based on your complaint, that's better. And so what I suggest, JAXsim reached 303 tests because while they were doing something, when they saw the occasion and when they saw the possibility that doing that was low effort, they put a test. Like they found a bug, let's put a test that in the future ensure that this bug will not happen. I'm doing a new piece of code, and so yeah, I already have some way of checking what that piece of code is doing, because you are writing a function, somehow you are running that function. Instead of doing a snippet of code that you just execute once and then you throw away, already write a test for running your function. It will be super complete, super covering everything. No, but you start. And then if you do that for some time, you end up with 303 tests. But let's not create a false dichotomy between not doing any testing or do super in-depth tests, because that typically blocks you from actually doing tests. Okay, thanks.
If I can, Carlos?
Yes.
Scusate. If I complement on what Silvio said, I totally agree. This 200 test for us was for free because we already had them due to JAXsim per se. But the idea is tests are needed. Even one test is better than nothing. And also for you to for instance, I think a lot of you, they merge things into bipedal locomotion. And every time there are things, do this test. This is the reason why we do these things, because it's quite easier than when you need to understand whether things are still functional to have unit tests, and it's easier to develop them all along the way. So as Silvio was saying, it's not 300 tests or nothing. There are middle way that are halfways that are really useful, and once you start with a good habit, it's really a small amount of work compared to what you gain then when you need to test and find bugs.
Okay, mine is more like a comment instead of a question. It's like I really like the output of the sprint, like you guys improving somehow the code, and I'm dealing with problems like moving a lot of images between CPU and GPU. There are many things that can be, let's say, optimized somehow. So I don't know which could be the space so we can kind of bunch of group with the people that are interested, kind of share kind of things that we have learned about it. We can all learn and how to optimize many things there.
Yeah, absolutely. I think also about software infrastructure for GPU learning is quite something. I'm looking at the learning Scrum Master now.
Yeah, I think I agree that. Really
now
nice.
I pass the ball to the learning Scrum Master, but I think also it could have a sense that this is also why I put them in the presentation, because if someone has told us before, I mean, we knew the CPU, but the way of could really have helped us. So let's try to share this knowledge and set it up. I agree.
Agree. Thank you.
Okay, one more question from Dani.
So, Carlotta, fantastic job. So, can you get back to the vision where you connect now all the things, human and etc. Yeah, the lesson. So, I just wanted to highlight two things. So, the first one is this sort of scheme. It's nice because it connects basically most of the activities we do in the lab. Okay, so we can basically fit any activity here from iFeel for estimating the human models, the human develop the models, to the walking, to the autonomy, because it can be put there to generate and parameterize models. So somehow this is basically somehow the vision that we are working on. So this is the first thing I wanted to highlight. The second thing I wanted to highlight is the importance of increasing complexity when needed. So there is that old way of saying that if you do not add things, probably you did not remove enough before. Okay, so clearly this does not always apply, but try to always understand to add complexity when it is needed. Okay, because otherwise you're going to pay a price. And the third thing I wanted to say, the importance of being incredibly focused. So having clear objectives and defining sprints, having clear objectives really help to increase the velocity of the entire team, whose sum is much greater than the individuals, by saying. Okay, so great. So with this, we go to lunch. For people from the cloud, so thank you very much. For those external to the AMI team, and for those internal, we meet together here at 2:30 by using the other link